Hello there, and welcome to Physics with William, where curiosity slows down just enough for us to examine it carefully. Tonight, we are turning our attention to a teenager. Not a king, not a general, not a famous inventor in his later years, but a 15-year-old student sitting with sheets of numbers in front of him. His name was Carl Friedrich Gauss, and before he was old enough to vote, travel freely, or even publish most of his ideas, he quietly began to understand something that had puzzled mathematicians for more than 2,000 years. Prime numbers. They are simple to define. A prime number is a whole number greater than 1 that can only be divided evenly by 1 and itself. 2, 3, 5, 7, 11. They appear straightforward, almost modest. Yet as numbers grow larger, primes seem to scatter unpredictably. No simple repeating pattern reveals where the next one will appear. They thin out, but not evenly. They surprise us. And that raises a question worth considering before we go any further. When you look at a list of numbers, do you expect order? Or do you expect randomness? If someone handed you a page filled with digits stretching into the thousands, would you assume there was a structure hidden inside, or would you think it was chaos? Take a moment and consider where you are right now. Are you at a desk, perhaps with a notebook nearby, on a train, sitting in a quiet room? And if you glanced at the time, what would it read? We measure our days by numbers constantly. We trust them. We rely on them. But we rarely question how deeply numbers themselves can hide patterns beneath what looks like disorder. If you find this kind of exploration steady and absorbing, feel free to like the video or subscribe. It helps this channel continue to examine scientific stories with patience and clarity. Now, let's return to a small German city in the late 18th century, where a young student began asking questions that most adults around him did not yet know how to answer. At first glance, nothing about prime numbers suggests mystery. Any child learning arithmetic can identify them, divide, and test. If no whole number other than 1 in itself fits evenly, the number is prime. The process is mechanical, reliable, almost tedious. Yet when mathematicians attempted to predict how many primes exist below a large number, they ran into difficulty. Suppose you want to know how many prime numbers are less than 100. That can be counted by hand. Less than 1,000? Still manageable with effort. But what about less than 1 million? Or 1 billion? The larger the boundary, the more complicated the question becomes. Ancient mathematicians had already proven that primes never run out. Euclid showed more than 2 millennia earlier that no matter how many primes you list, there is always another. His proof was elegant and decisive. However, it did not answer how primes are spaced. It confirmed infinity, but not distribution. By the 18th century, mathematicians across Europe had compiled extensive tables of primes. They listed them carefully, sometimes up to tens of thousands. These tables were practical tools for number theory, but they also revealed something unsettling. Primes did not appear at regular intervals. The gaps between them grew larger as numbers increased, but unevenly. Sometimes 2 primes would sit close together. Other times, long stretches of composite numbers appeared with no primes at all. This irregularity suggested randomness, yet the overall thinning hinted at structure. As numbers grow, primes become less frequent. That much was clear. But how much less frequent? And could it be described precisely? Such questions might not seem urgent outside mathematics. They do not directly affect farming or trade in the 18th century. But within mathematics, understanding primes was considered fundamental. Primes are the building blocks of all whole numbers. Every integer can be broken down into prime factors. In that sense, primes are like atoms in chemistry. If you want to understand numbers fully, you must understand primes. Now imagine being 15 years old and encountering this problem. No formal degree, no published papers, just curiosity and a willingness to examine long columns of numbers. Gauss grew up in Brunswick in what is now Germany. His family was not wealthy. His father worked as a labourer and was known to be strict and practical. Formal education beyond the basics was not guaranteed. Yet Gauss displayed unusual talent from an early age. Stories circulated about him correcting arithmetic mistakes made by adults. Whether every detail of those stories is accurate matters less than the broader truth. Teachers recognized quickly that his abilities were exceptional. By adolescence, Gauss had access to mathematical text far beyond standard school material. He began studying number theory independently, and number theory at the time was not a polished, complete field. It was fragmented, full of open problems. Prime numbers were among its central mysteries. Some historians suggest that around the age of 15, Gauss began examining prime tables with unusual intensity. He did not merely list primes, he counted them. He tracked how many primes appeared below certain numbers, below 100, below 1,000, below 10,000. Instead of focusing on individual primes, he focused on their density. Consider what that shift represents. Rather than asking, "Is this number prime?" he asked, "How many primes are there up to this point?" That question transforms the problem. It moves from individual instances to overall behaviour. Let's try to see the problem as he might have. Suppose you list the first few primes: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Below 10, there are 4 primes. Below 100, there are 25 primes. Below 1,000, there are 168 primes. Already you notice something. The numbers increase, but the rate slows relative to the size of the boundary. Primes become less common compared to the total pool of numbers. If primes were evenly spaced, you could expect a simple ratio, but they are not. So Gauss began searching for a function, a mathematical expression, that could approximate how many primes exist below a given number. At 15, most students are memorizing formulas. Gauss was looking for one that no one had yet discovered. There is evidence from his later notes that by his teenage years, he had developed an intuition that the number of primes less than a large number n is approximately equal to divided by the natural logarithm of n. In modern notation, this is written as n over ln of n. Today, this relationship is known as the Prime Number Theorem, though it would not be formally proven until nearly a century later. Pause for a moment and reflect on what that means. A teenager, working without modern computational tools, identified a pattern involving logarithms, a relatively advanced mathematical concept at the time, to describe the distribution of prime numbers across the entire number line. Logarithms are functions that grow slowly, much more slowly than linear functions. If primes thin out according to a logarithmic relationship, that implies a specific kind of order. Not random scattering, not simple spacing, but a thinning governed by a precise mathematical law. How could he have guessed this? He examined data, he counted, he compared ratios. For increasingly large values of n, he likely computed the ratio of n to the number of primes below n. He observed how that ratio behaved. Gradually, patterns emerged. This was not mystical insight. It was careful observation combined with exceptional mathematical instinct. Gauss did not immediately publish this idea. In fact, he was known throughout his life for withholding results until he considered them fully developed. He preferred certainty over speculation. But in his personal notes, the insight was recorded. At 15, he was not yet the famous mathematician history remembers. He was a student with access to books and a mind inclined towards structure. Yet the seeds of a law governing prime numbers were already forming, and here is where the story deepens. Because discovering a pattern is one thing, understanding why it holds is another. The idea that primes follow a logarithmic distribution suggests a connection between multiplication, growth rates, and the structure of numbers themselves. That connection would later tie into complex analysis, a branch of mathematics involving imaginary numbers and intricate functions defined over the complex plane. None of that would have been visible in full clarity to a teenager. What he had was intuition backed by calculation. He sensed regularity and apparent irregularity. He saw trend where others saw randomness. When we examine breakthroughs in science, we often focus on the moment of public recognition. The published paper, the formal proof, the award. But in this case, the critical insight occurred quietly, years before the mathematical community fully understood its significance. The idea that primes obey a statistical law rather than a simple repeating pattern was revolutionary. It suggested that mathematics contains phenomena that resemble probability, even though primes are deterministic. Each number is either prime or not. There is no chance involved. Yet when viewed collectively, their behaviour resembles a distribution. That duality, deterministic at the micro level, statistical at the macro level, would later become a central theme in mathematics and physics alike. At 15, Gauss could not have known how far this line of thinking would extend, but he recognised that prime numbers were not merely isolated curiosities, they followed a deeper structure. As we continue examining his early years, it becomes important to understand the environment that allowed such thinking to develop. Brunswick was not Paris or London. It was a modest German state, yet it provided access to libraries and teachers who recognised Gauss's potential. One of his mentors helped secure financial support for his education, allowing him to continue studying rather than entering manual labour. Without that intervention, the history of mathematics might look different. There is also something worth noting about age. Youth is often associated with speed and boldness, but Gauss's work on primes required patience. It required counting, verifying, comparing. It required resisting the temptation to jump to conclusions. When you look at a long list of numbers, patterns can appear where none exist. Humans are skilled at seeing structure even in noise. Distinguishing genuine regularity from coincidence demands discipline. The fact that Gauss's conjecture later proved accurate indicates that his judgment was precise. We are still at the beginning of this story. The insight into the distribution of primes did not immediately reshape mathematics. It remained largely private, but it set the stage for developments that would unfold over decades. In order to appreciate how unusual this was, we need to step back further and examine what mathematicians before Gauss understood about prime numbers and what tools they had available. Because the teenage insight did not emerge in isolation. It grew out of centuries of accumulated effort, partial results, and unanswered questions, an understanding that broader landscape makes the achievement at 15 not just impressive, but extraordinary. In 1777, in the small German city of Brunswick, a child was born into a household that had no expectation of producing one of the greatest mathematicians in history. Carl Friedrich Gauss entered the world on April 30th, the son of Gebhard Dietrich Gauss and Dorothea Benze. His father worked in various practical trades, gardening, masonry, bookkeeping, anything that provided steady income. His mother came from a poorer background and had little formal education. Neither parent had advanced schooling, and there was nothing in the family history that suggested the emergence of a prodigy. Brunswick in the late 18th century was not a centre of global intellectual life. It was a modest duchy within the fragmented territories of what would later become Germany. Political power was divided among numerous states. Universities existed, but intellectual exchange moved more slowly than it would in the centuries to come. A child born there might grow up to manage land, join a trade, or serve in administration. The idea that one would uncover a fundamental law about prime numbers before reaching adulthood would have seemed unlikely. Yet from an early age, Gauss demonstrated unusual facility with numbers. Stories about his childhood circulate widely, and while some have undoubtedly been polished by repetition, the consistency across accounts suggests a genuine pattern. He displayed a natural ability to compute mentally, to notice errors in arithmetic, and to retain numerical information with precision. These were not isolated incidents, but recurring observations from those around him. One well-known anecdote describes his father calculating wages for labourers and making a minor arithmetic mistake. The young Gauss, still a small child, reportedly corrected him without hesitation. Whether every detail of that event unfolded exactly as later told is less important than what it reveals. Numbers were not foreign symbols to him. They were familiar, almost intuitive. Formal education began early. Brunswick maintained local schools where children learned reading, writing, and arithmetic. Gauss attended one such school under the supervision of a teacher named Johann Büttner. It was there that another frequently cited episode occurred. The class was assigned the task of summing the integers from 1 to 100, a tedious exercise intended to occupy students quietly. Instead of adding sequentially, Gauss quickly identified a pattern, pairing numbers from opposite ends of the sequence, 1 and 100, 2 and 99, 3 and 98, each pair summed to 101. With 50 such pairs, the total became 50 multiplied by 101, which equals 5050. He presented the result almost immediately. The significance of that moment lies not in the speed of calculation alone, but in the structural thinking it demonstrates. Rather than performing repetitive addition, he reorganized the problem. He saw symmetry where others saw sequence. This approach, reframing questions to expose underlying order, would characterize his later work on prime numbers and many other areas of mathematics. His teacher recognized that ordinary lessons would not be sufficient. Advanced material was introduced. The Duke of Brunswick, informed of the boy's talent, eventually provided financial support for his education. This patronage was crucial. Without it, Gauss might have been required to enter a trade early, limiting his opportunity for sustained study. Education in late 18th century Germany emphasized classical languages, philosophy and mathematics for those pursuing higher learning. Gauss excelled across subjects but showed particular affinity for mathematics. He absorbed textbooks quickly and began reading beyond assigned material. Works on number theory, then still an evolving field, captured his interest. To understand the intellectual environment he encountered, consider the state of mathematics at the time. Isaac Newton and Gottfried Wilhelm Leibniz had developed calculus in the previous century. Leonhard Euler had expanded number theory and analysis with prolific contributions. Yet prime numbers remained elusive. They were recognized as foundational, but no comprehensive theory described their distribution. By adolescence, Gauss was studying independently at a level comparable to university students. He entered the Collegium Carolinum in Brunswick, an institution positioned between secondary school and university. There he encountered more advanced mathematical works. He later attended the University of Göttingen, though he often preferred solitary study to lectures. The image of Gauss as a quiet student poring over tables of numbers is not exaggerated. He maintained notebooks, most notably his mathematical diary, in which he recorded discoveries succinctly. Entries were brief, often cryptic, but they demonstrate continuous engagement with deep problems. Prime numbers drew his attention early. At that stage in his life, number theory was not the dominant field it would later become. Many mathematicians focused on geometry, mechanics, and astronomy. Yet Gauss gravitated toward the arithmetic properties of integers. There is something revealing in that choice. Primes are abstract. They do not correspond directly to physical measurement. Studying them requires comfort with pure structure. What might have motivated a teenager to examine prime tables so carefully? Part of the answer lies in curiosity about patterns. Consider again the list of primes below 100. The gaps between them vary. 2 and 3 are consecutive integers, separated by 1. Then comes a gap of 2 between 3 and 5, another gap of 2 between 5 and 7, then a gap of 4 between 7 and 11. As numbers increase, gaps sometimes widen significantly. No simple arithmetic progression captures their spacing. For someone inclined toward order, this irregularity poses a challenge. Are primes random, or is there a hidden law governing their frequency? Gauss approached this question quantitatively. Instead of analysing individual gaps alone, he counted cumulative totals. How many primes lie below 1,000? Below 10,000? He examined ratios between the boundary number and the count of primes. These ratios suggested that primes become rarer in a predictable way. The critical observation was that the density of primes near a large number n appears roughly proportional to 1 divided by the logarithm of n. In modern language, the number of primes less than n approximates n divided by ln n. For a 15-year-old to even consider logarithms in this context indicates both exposure to advanced mathematical tools and the capacity to apply them creatively. It is important not to romanticize this process as sudden revelation. The evidence suggests gradual development. Gauss compiled data, tested approximations, and refined his understanding. He did not publish a bold announcement declaring a theorem. Instead, he recorded his insight privately. His temperament contributed to this restraint. Gauss preferred certainty over speculation. He often withheld publication until he possessed rigorous proof. This habit sometimes frustrated contemporaries who later rediscovered results he had already established. In the case of prime distribution, he recognized the pattern long before a formal proof was achieved by others in the 19th century. Returning to Brunswick, one can imagine the contrast between the city's modest surroundings and the scale of the questions forming in his mind. Streets of stone and timber houses framed a life that outwardly resembled many others. Yet internally, Gauss was contemplating the structure of the infinite number line. Support from the Duke enabled further study, but intellectual growth still depended largely on personal discipline. There were no modern computers to calculate prime counts quickly. Every table required manual verification. Errors could mislead conclusions. Sustained attention was essential. This patience distinguished Gauss from many prodigies whose talents burn brightly but briefly. He did not rely on intuition alone. He combined it with verification. When patterns appeared, he tested them. When approximations worked for small values, he extended them to larger ones. Consider the conceptual shift involved in approximating prime counts. Exact formulas were unavailable. Instead, Gauss accepted that a function might describe primes statistically rather than deterministically. This approach anticipates later developments in analytic number theory, where averages and asymptotic behavior matter as much as exact values. Such thinking was unusual for a teenager. Most students focus on solving assigned problems. Gauss was formulating new ones. He was not content to know that primes are infinite. He wanted to understand how they are distributed across the entire sequence of natural numbers. Brunswick itself, though not intellectually dominant, provided relative stability. Political upheaval would later reshape Europe through the Napoleonic Wars, but during Gauss's youth, his primary environment remained conducive to study. Access to books and mentorship played decisive roles. One should also acknowledge his mother's influence. Though not formally educated, Dorothea supported her son's studies. Later accounts suggest she was proud of his achievements and encouraged his intellectual pursuits. Family backing, even if not scholarly, can foster confidence. As Gauss matured, he began corresponding with other mathematicians. Exposure to broader discourse reinforced his ambitions. Yet even before establishing a network, the core ideas about primes had already begun forming. The broader question underlying his teenage investigations can be framed simply. If primes appear irregular, is that irregularity only superficial? When examined over large scales, does order emerge? He suspected that it does. This suspicion did not remain idle curiosity. It shaped subsequent decades of mathematical exploration, not only for Gauss, but for others who followed. Adrien-Marie Legendre independently proposed similar approximations for prime distribution. Later, in the 19th century, Jacques-Yad Ahmad and Charles-Jean de la Vallée-Poussin would prove the prime number theorem rigorously. But during those later triumphs, the initial intuition traced back to notes written by a young student in Brunswick. Understanding the boy's environment clarifies how remarkable that trajectory was. No inherited wealth guaranteed extended leisure. No institutional prestige predestined recognition. Instead, talent combined with support and disciplined curiosity. The city itself did not change dramatically because of his teenage insight. Life continued. Markets opened. Church bells rang. Yet within a notebook, a line of reasoning was taking shape that would eventually define a cornerstone of number theory. Examining his early years also highlights a pattern in scientific history. Major ideas often originate quietly. They do not announce themselves with ceremony. A student works through data. A ratio suggests itself. A function seems to fit. The significance becomes visible only later. In Gauss's case, the discovery concerning primes was not isolated from his other achievements. During his youth and early adulthood, he contributed to algebra, astronomy, geometry, and statistics. His capacity for abstraction extended across domains. But prime numbers retained a central place in his intellectual life. They represented the simplest objects with the most complex behavior. As his education progressed beyond Brunswick, his analytical tools expanded. University study deepened his understanding of calculus and analysis, providing formal frameworks that would later connect directly to prime distribution through complex functions. The teenager counting primes would become the mathematician investigating deep properties of logarithms, integrals, and analytic continuation. The seeds planted in Brunswick would grow into a broader theory. Before reaching that stage, however, the mathematical community itself must be considered. What exactly did scholars know about primes before Gauss refined his insight? How close were they to articulating a law? And how did earlier efforts shape the problem he encountered as a student? Stories about childhood prodigies often grow in the telling. Details become sharper, dialogue more polished, the timing more dramatic. Yet in the case of Carl Friedrich Gauss, one classroom episode has persisted for more than 2 centuries, repeated in biographies, lectures, and mathematics textbooks. Whether every word unfolded exactly as later described is impossible to confirm. What can be confirmed is that the story reflects something real about how his mind worked. The setting was a primary school in Brunswick. The teacher, Johann Büttner, was responsible for managing a room full of young students at different levels of ability. Teaching arithmetic in the late 18th century involved repetition. Students copied numbers, performed long additions, and practiced memorizing multiplication tables. Maintaining order required giving tasks that would occupy everyone simultaneously. According to the account, Büttner once assigned the class the problem of adding all the integers from 1 to 100. The expectation was clear. Each student would write the sequence and add it step by step. It was a long sum, enough to keep the class quiet for a considerable time. Most students began the straightforward way. 1 plus 2 equals 3, 3 plus 3 equals 6, 6 plus 4 equals 10, and so on, slowly accumulating the total. Gauss, however, reportedly placed his slate down after only a short time and presented the answer: 5050. The key is not the speed alone, it is the method he used. Instead of adding sequentially, he observed symmetry within the sequence. The first and last numbers summed to 101. The second and second to last also summed to 101. In fact, every pair formed by taking one number from the beginning and one from the end equals 101. 1 plus 100 equals 101 plus 99 equals 101 plus 98 equals 101. There are 50 such pairs. Multiply 50 by 101 and the total is 5050. What this demonstrates is structural recognition. Rather than treating the problem as a list of individual operations, he saw the entire arrangement at once. He reorganized it mentally into a simpler pattern. This pattern can be generalized. The sum of the first n integers equals n multiplied by n plus 1 divided by 2. In this case, n equals 100. So 100 times 101 divided by 2 equals 5050. Today this formula is introduced early in algebra courses. For Gauss, it emerged naturally from examining the structure of the sequence. Why does this classroom anecdote matter in the context of prime numbers? Because the intellectual move is the same. In both cases, Gauss confronted a collection of numbers that appeared tedious or irregular. Instead of accepting their surface appearance, he searched for underlying organization. With the sum from 1 to 100, he recognized symmetry. With prime numbers, he sought statistical regularity within apparent randomness. In a typical arithmetic classroom, students follow procedures. They apply learned steps. Gauss demonstrated something different. He questioned the procedure itself. He asked whether the structure of the numbers could simplify the task. The environment of the classroom likely amplified the impression. Other students were still working methodically through additions when he had already finished. The teacher, expecting a long period of quiet calculation, was confronted instead with an immediate solution. Whether Büttner reacted with surprise or skepticism, it became clear that the boy required more advanced material. Repetition would not develop his abilities. The broader educational system of the time did not specialize in nurturing exceptional mathematical talent. Resources were limited. Instruction was often rigid, yet individual teachers could make decisive differences. Recognizing Gauss's aptitude, Büttner reportedly recommended him for further support. It is also important to avoid exaggeration. Solving the sum from 1 to 100 quickly does not, by itself, predict the discovery of a law governing prime numbers. Many students today can learn that formula. What distinguishes Gauss is not one clever trick, but the consistent pattern of thinking it represents. Consider again the structure of prime numbers. At first glance, primes lack symmetry. They are scattered unevenly across the number line. But if you step back and consider larger intervals, you may begin to see trends. The density decreases gradually. The frequency can be approximated. A larger pattern emerges when viewed from the right perspective. The classroom story illustrates his instinct to step back. There is another dimension worth considering. Many accounts describe Gauss as confident but reserved. He did not seek attention for dramatic effect. Presenting the answer early was not an act of performance. It was simply the natural consequence of his method. This temperament influenced his later work. When he conjectured that the number of primes less than n is approximately n divided by the natural logarithm of n, he did not rush to publish. He tested the idea. He verified it against data. He recorded it privately in his diary. The same discipline visible in the classroom, clarity without spectacle, characterized his mature mathematics. To appreciate how unusual this was, imagine the intellectual climate of the time. Calculations were performed by hand. Errors were common. Mathematical notation was less standardized than today. Access to extensive tables required effort. Identifying patterns demanded patience. When Gauss later examined prime tables, he approached them not as isolated entries but as components of a larger structure. Instead of asking, "Is 997 prime?" he asked, "How many primes appear below 1000? And further, how does that count compare with values predicted by a simple function?" The classroom episode provides a small-scale example of this shift in thinking. There is also a psychological component. Some children develop comfort with patterns early. They see relationships intuitively. Others rely more heavily on memorized steps. Gauss belonged firmly to the first category. He did not merely memorize formulas, he derived them. One could argue that the arithmetic anecdote is less about genius and more about perspective. The problem assigned by the teacher contained hidden symmetry. Anyone trained to look for it could find it. What distinguished Gauss was that he looked. Prime numbers present a harder challenge because the symmetry is not obvious. There is no simple pairing that reveals their distribution. Instead, the structure appears only when examining cumulative counts and logarithmic relationships. Recognizing that required abstraction beyond elementary arithmetic. Still, The intellectual habit was the same: reorganize the data until order becomes visible. The classroom setting also highlights the importance of environment. If Büttner had dismissed the quick answer as disruptive or incorrect, progress might have slowed. Instead, recognition led to opportunity. Support from the Duke of Brunswick followed. Access to advanced study became possible. Educational systems often struggle to balance uniform instruction with individual development. Gauss benefited from a teacher who noticed the difference between impatience and insight. As he advanced in his studies, the arithmetic of sequences expanded into the arithmetic of primes. Instead of adding consecutive numbers, he counted primes within intervals. Instead of pairing 1 and 100, he compared n to log base e of n. Instead of multiplying 50 by 101, he divided n by a logarithmic function. These moves differ in complexity but share conceptual DNA. There is an additional lesson embedded in this story. Mathematics rewards reorganization. A problem rarely changes. Perspective does. In the classroom, the numbers 1 through 100 were fixed. Gauss changed how they were arranged in his mind. With primes, the sequence of natural numbers remains fixed. He changed how he viewed their density. Many later mathematicians would confront the same problem of prime distribution. Adrien-Marie Legendre proposed approximations. Others refined estimates. Eventually, in the 19th century, Jacques Hadamard and Charles-Jean de la Vallée-Poussin established rigorous proofs using complex analysis. Yet the intuitive spark appeared decades earlier in a notebook belonging to a former classroom prodigy. It is tempting to isolate the anecdote as a charming origin story, but it serves a deeper function. It shows that the capacity for structural thinking was present early and consistently. The same mind that paired 1 with 100 would later pair n with ln of n. When considering intellectual development, continuity matters more than isolated brilliance. Gauss did not transform overnight from quick calculator to master theorist. The transition unfolded gradually, rooted in habits formed in childhood classrooms. Imagine the scene once more: rows of desks, chalk dust, the teacher expecting prolonged silence, a young student reorganizing numbers mentally and arriving at a result within moments. That same quiet reorganization would later apply to pages filled with primes. The arithmetic exercise had a definite answer. Prime distribution did not, at least not initially. There was no teacher waiting with a solution key. The challenge extended beyond routine computation into conjecture. And that shift, from solving assigned problems to formulating new ones, marks the true beginning of Gauss's contribution to number theory. By the time he entered higher education, he had already internalized the lesson: do not accept surface complexity. Search for structure, test it, refine it, confirm it. Prime numbers would become the arena in which this method reached new depth. Before examining the broader mathematical landscape he inherited, it becomes useful to understand precisely what earlier thinkers had discovered about primes and why their insights stopped short of the law Gauss sensed as a teenager. By the time Carl Friedrich Gauss was entering adolescence, Europe had already undergone more than a century of intellectual transformation. The period we now call the Enlightenment had reshaped how scholars approach knowledge. Authority based on tradition or hierarchy was increasingly challenged by evidence, calculation, and reason. Mathematics, in particular, had moved from a specialized scholarly pursuit to a central tool for understanding nature. To understand the significance of Gauss's early work on prime numbers, it is necessary to examine the environment into which he was born. The Enlightenment was not a single movement directed by one institution. It was a broad cultural shift that affected philosophy, science, politics, and education. In the 17th century, figures like Isaac Newton had demonstrated that mathematical laws could describe the motion of planets with extraordinary precision. By the 18th century, the success of mathematics and physics encouraged scholars to believe that rational structure underlay much of reality. This belief shaped educational institutions. universities across Europe increasingly emphasized mathematical training. Astronomy, mechanics, navigation, and engineering depended on accurate calculation. Governments recognized the practical value of scientific expertise, especially for military and economic purposes. Yet number theory, the study of whole numbers and their properties, occupied a more ambiguous position. It was admired for its elegance but lacked immediate application in industry or warfare. Prime numbers did not guide ships across oceans or determine artillery trajectories. They seemed abstract, almost recreational compared to the urgent demands of applied mathematics. Still, intellectual curiosity about primes persisted. Earlier mathematicians had laid foundations that would influence Gauss's thinking. Euclid had proven in antiquity that primes are infinite. Pierre de Fermat in the 17th century had posed challenging conjectures about primes, some unsolved for centuries. Leonhard Euler expanded number theory by linking prime numbers to infinite series and analytic methods. Euler's work was particularly important. He demonstrated that the harmonic series of reciprocals of primes diverges, meaning that primes, though thinning out, do not vanish too quickly. He also developed relationships between primes and the zeta function, an object that would later become central in analytic number theory. However, Euler did not establish a precise law describing how many primes lie below a given large number. The Enlightenment atmosphere encouraged systematic cataloguing. Tables of logarithms were constructed to aid computation. Astronomical observations were recorded meticulously. Prime tables fit naturally into this culture of compilation. Mathematicians listed primes up to tens of thousands, sometimes higher, verifying each entry by hand. These tables revealed two simultaneous truths. First, primes never disappeared entirely. Second, they became less frequent as numbers grew. The larger the number, the wider the typical gap between consecutive primes. Yet no formula predicted their exact positions. In France, Britain, Germany, and Italy, mathematical societies formed networks of correspondence. Letters circulated between scholars discussing problems and solutions. Intellectual life increasingly crossed political boundaries, even as Europe remained divided into rival states. Germany itself was not unified. It consisted of numerous principalities and duchies, including Brunswick, where Gauss grew up. Political fragmentation did not prevent intellectual exchange, but sometimes slowed institutional development. Paris and London hosted prominent academies, while smaller German states relied more on local patronage. The Duke of Brunswick's support for Gauss reflects this structure. Talented individuals often depended on aristocratic sponsorship rather than national research institutions. Without such backing, extended study could become financially impossible. Meanwhile, philosophical currents shaped scientific thinking. Rationalism and empiricism influenced how scholars interpreted patterns. The idea that nature obeys laws encouraged mathematicians to search for similar regularities within abstract systems. If planetary motion follows precise equations, perhaps the distribution of prime numbers also follows a hidden law. Yet there was tension between determinism and unpredictability. In mechanics, Newton's equations produced clear predictions. In number theory, primes resisted simple description. They appeared deterministic. Each number is definitively prime or composite, but collectively irregular. The Enlightenment fostered confidence in reason. It also cultivated patience in investigation. Scholars were willing to collect extensive data before proposing general principles. This method suited Gauss's temperament. When he later examined prime counts, he followed a tradition of careful compilation combined with analytical reasoning. Another aspect of the era deserves attention: the development of logarithms. Introduced in the early 17th century by John Napier, logarithms simplified multiplication and division. By Gauss's time, logarithmic tables were standard tools in calculation. Understanding logarithms required familiarity with exponential growth and inverse relationships. The connection between logarithms and primes was not immediately obvious. Logarithms were practical aids for computation. but their mathematical properties, slow growth relative to linear functions, made them suitable for approximating quantities that decrease in density gradually. Gauss's insight that prime distribution relates to the natural logarithm reflects his command of advanced analytical tools for his age. In addition to mathematical developments, political and social changes influenced education. The Enlightenment emphasized literacy and structured schooling. Even modest cities like Brunswick maintained institutions where talented students could advance beyond basic instruction. However, access to advanced study remained limited. Many children left school early to work. Gauss's continuation in education was not inevitable. Patronage allowed him to remain in academic environments long enough to explore deeper questions. Across Europe, revolutions were reshaping political structures. The American Revolution had recently concluded. The French Revolution would begin when Gauss was a teenager. These upheavals disrupted institutions, but also spread Enlightenment ideals about reason and equality. Mathematics, though seemingly insulated from politics, was not entirely detached. National academies funded research. Governments valued navigational accuracy and artillery precision. Yet pure number theory remained somewhat peripheral to state priorities. That peripheral status may have benefited Gauss. Without pressure for immediate application, he could pursue abstract questions. Prime distribution did not need to produce practical results to justify study. The intellectual culture also prized rigorous proof. By the late 18th century, mathematicians expected logical completeness. Conjectures required demonstration. This expectation explains why Gauss hesitated to publish his approximation for prime distribution without proof. He recognized the importance of verification within the prevailing standards of scholarship. At the same time, informal conjecture circulated widely. Adrien-Marie Legendre proposed an approximation for the number of primes less than n, involving n divided by the logarithm of n minus a constant. Whether Legendre was influenced by Gauss's earlier notes remains debated, but similar ideas were emerging in multiple places. The problem was ripe for solution. Europe's Age of Enlightenment thus provided both the tools and the mindset necessary for Gauss's discovery. Mathematical notation had matured. Logarithms were well understood. Tables of primes were available. The expectation that hidden laws govern patterns encouraged systematic investigation. Still, recognizing a law required individual initiative. Many mathematicians had access to the same tables Gauss examined. Few perceived the logarithmic pattern as clearly or as early. There is also the question of intellectual isolation. While correspondence networks existed, information travelled slowly. Gauss's early conjecture appears to have been largely independent. He was not responding to a published theorem, but exploring data personally. The Enlightenment valued independence of thought. Scholars increasingly trusted their own reasoning over inherited authority. Gauss embodied this principle. Even as a teenager, he did not accept primes as inexplicable irregularities. He assumed structure existed and sought it. Education at the University of Göttingen further immersed him in advanced mathematics. Göttingen would later become a global centre of mathematical research, but even in Gauss's time, it provided access to leading works. Exposure to analysis, calculus, and algebra equipped him to articulate relationships beyond arithmetic. The Enlightenment also encouraged classification. Naturalists categorized plants and animals. Chemists organized elements. Mathematicians classified functions and equations. Prime numbers, as fundamental components of integers, invited classification as well. Counting primes below various thresholds resembled counting species within ecological zones. This classificatory impulse aligns with Gauss's approach. He did not attempt to predict each prime individually. Instead, he categorized them collectively by density. As Europe moved toward the 19th century, the momentum of Enlightenment rationalism would evolve into Romanticism and new philosophical movements. Yet mathematics retained its commitment to clarity and proof. Gauss would later contribute to multiple fields: astronomy, statistics, complex analysis, reinforcing the error's belief in systematic reasoning. At 15, however, he was not yet a central figure in European intellectual life. He was a student shaped by Enlightenment ideals, benefiting from patronage, and working within a culture that believed patterns could be discovered through disciplined inquiry. Prime numbers represented a frontier. They were ancient objects studied since Greek antiquity, yet their large-scale behaviour remained uncertain. The tools to investigate them had matured, but the final connection between logarithms and prime density awaited articulation. Within this broader European context, Gauss's early conjecture appears less like isolated genius, and more like a convergence of preparation and perception. The environment supplied tables, logarithms, and analytic techniques. His temperament supplied persistence and structural insight. To appreciate fully what he accomplished, it becomes necessary to examine the object of his curiosity directly. Before exploring how he analysed prime tables, one must clarify what prime numbers are, why they matter, and why their distribution posed such a persistent challenge. Before examining how a teenager in Brunswick began to approximate the distribution of primes, it is necessary to clarify what prime numbers actually are and why they occupy such a central place in mathematics. The definition is simple. A prime number is a whole number greater than one that has exactly two positive divisors, 1 and itself. That means it cannot be broken down into smaller whole number factors. 2 is prime, 3 is prime, 4 is not, because it can be divided evenly by 2. 5 is prime. 6 is not, because it equals 2 multiplied by 3. The pattern continues. At first glance, this may seem like a narrow category within arithmetic. There are infinitely many whole numbers, and primes represent only a subset. Yet this subset plays a foundational role. Every whole number greater than 1 can be expressed as a product of prime numbers. This fact is known as the fundamental theorem of arithmetic. For example, 12 equals 2 times 3, 30 equals 2 times 3 times 5, 77 equals 7 times 11. No matter how large a number becomes, it can be broken down uniquely into primes, aside from the order in which those primes are written. In that sense, primes are the basic building blocks of all integers. They are not just another group within arithmetic, they are the structural components from which all composite numbers are assembled. This structural role explains why primes fascinated mathematicians long before Carl Friedrich Gauss began examining them. If one wishes to understand the nature of numbers themselves, one must understand the pieces from which they are constructed. However, identifying whether a specific number is prime becomes increasingly difficult as numbers grow larger. For small values, divisibility tests are straightforward. To check if 29 is prime, one can test divisibility by 2, 3, 5, and so on up to its square root. It turns out 29 is prime. But what about 10,007? Or 1,000,003? The larger the number, the more checks are required. Before modern computers, verifying primality for large numbers demanded patience and organisation. Even so, the problem of identifying individual primes is not the deepest mystery. The deeper question concerns distribution. How frequently do primes appear as numbers increase? Is there a rule governing how often they occur? Consider the first few natural numbers. 1 is neither prime nor composite. 2 is prime, 3 is prime, 4 is composite, 5 is prime, 6 is composite, 7 is prime, 8 is composite, 9 is composite, 10 is composite. In the first 10 numbers, 4 are prime. That seems relatively dense. Between 1 and 100 there are 25 primes. Between 1 and 1000 there are 168 primes. Already the proportion decreases. In the first 10 numbers, primes account for 40%. In the first 100 they account for 25%. In the first 1000, about 16.8%. The pattern suggests that primes become less common as numbers grow larger. But how much less common? And how precisely does that decrease occur? It is easy to see that primes thin out. Even without advanced theory, one can observe that large numbers have more potential divisors. A number around 10 has only a few smaller integers to test as factors. A number around 1000 has many more possible divisors. The probability that a large number will share a factor with some smaller number increases. Yet this reasoning is only qualitative. It does not produce a formula. To move from observation to law, mathematicians began counting primes systematically. Let pi of n represent the number of primes less than or equal to n. For example, pi of 10 equals 4, pi of 100 equals 25, p of 1000 equals 168 pi of 10,000 equals 1229. As n increases, p of n increases as well, but at a slower rate relative to n itself. The crucial question becomes, can pi of n be approximated by a simple expression involving n? If primes followed a regular pattern, say, every fifth number beyond a certain point, the answer would be trivial, but they do not. Gaps between primes vary. Sometimes primes appear in pairs separated by only 2 units, such as 11 and 13. These are called twin primes. At other times, long stretches of composite numbers intervene. For instance, between 89 and 97, there is a gap of 8. As numbers grow larger, gaps occasionally stretch even further. Yet no finite gap can eliminate primes entirely, because Euclid proved that there are infinitely many. This dual nature, local irregularity combined with global persistence, makes primes particularly challenging. Now consider another perspective. Instead of asking whether a specific number is prime, ask what fraction of numbers near n are prime. If one examines numbers around 100, roughly 1 in 4 is prime. Around 1000, roughly 1 in 6 is prime. Around 1 million, roughly 1 in 14 is prime. This gradual thinning suggests that the density of primes decreases slowly but steadily. The key word here is slowly. If prime density decreased linearly, if, for example, the proportion dropped by a fixed percentage every 1,000 numbers, then primes would eventually vanish, but they do not. The decrease is much more gradual. Logarithms enter the picture precisely because they grow slowly. The natural logarithm function, ln of n, increases without bound but at a decreasing rate. Dividing n by ln n produces a function that increases roughly in line with the count of primes below n. This is the central insight that Gauss would articulate privately in his youth. But to appreciate its significance, one must recognize how unexpected it was. Nothing in the definition of primes mentions logarithms. Nothing about divisibility tests hints at exponential growth or analytic functions. The connection arises only when examining cumulative behavior over large scales. There is another way to understand why primes thin out. Imagine selecting a large number at random. The probability that it is divisible by 2 is about 1/2. The probability that it is divisible by 3 is about 1/3. Divisible by 5, about 1/5. To be prime, a number must avoid divisibility by all smaller primes. A rough heuristic argument suggests that the chance a number near n is prime should be related to the product of probabilities that it is not divisible by smaller primes. This reasoning, when refined carefully, leads toward the 1 over natural log of n relationship. However, this reasoning is not straightforward. It involves subtle interactions between divisibility conditions. That subtlety explains why it took centuries for a precise statement, the Prime Number Theorem, to be proven rigorously. The theorem states that as n becomes very large, the ratio of pi of n to n over log of n approaches 1. In other words, n over the natural logarithm of n becomes an increasingly accurate approximation for the number of primes less than n. To see this numerically, consider n equals 1000. The natural logarithm of 1000 is approximately 6.907. Dividing 1000 by 6.907 gives about 144.8. The actual number of primes below 1000 is 168. The approximation is not perfect but reasonably close. for n equals 1 million, ln n is about 13.815. Dividing gives approximately 72,382. The actual count of primes below 1 million is 78,498. Again, the approximation improves as n grows larger. This increasing accuracy for larger values is characteristic of asymptotic laws. They do not match small numbers perfectly, but converge toward truth as scale increases. For a 15-year-old to suspect such behavior required moving beyond arithmetic into analysis. It required comparing counts with logarithmic functions and recognizing convergence. But before returning to Gauss's notebook, it is useful to reflect on why primes resist simple formulas. There is no known elementary expression that generates exactly the sequence of prime numbers and nothing else. Polynomials fail. Linear patterns fail. Even sophisticated formulas often produce composites along with primes. The unpredictability of individual primes contrasts sharply with the predictability of their overall density. That contrast is central to modern number theory. Deterministic rules at the micro level produce statistical regularity at the macro level. This dual character appears in other areas of mathematics and science. In physics, the motion of individual gas molecules is complex, yet temperature and pressure follow simple laws. In probability theory, random events produce stable averages. Prime numbers, though not random, display behavior reminiscent of statistical systems when viewed collectively. Understanding primes, therefore, is not merely about divisibility. It is about recognizing patterns that emerge from complexity. In Gauss's time, the absence of a precise law for pi of n represented a gap in number theory. Mathematicians could prove infinite existence and establish certain bounds, but they lacked an asymptotic formula. Gauss's early insight did not come with a proof. It came with conviction based on calculation. He had examined enough data to believe that n over ln n captured the trend accurately. To reach that belief, he needed both computational discipline and conceptual flexibility. He had to be comfortable manipulating logarithms and comparing ratios. He had to recognize that primes thin out not linearly, not exponentially, but logarithmically. This distinction matters. Linear decay would eliminate primes eventually. Exponential decay would eliminate them even faster. Logarithmic decay ensures their persistence, albeit sparsely. In summary, prime numbers are simple in definition, but complex in behavior. They are the fundamental units of multiplication. They appear irregular when viewed individually, but follow a precise statistical law when viewed collectively. The next step in this story involves looking backward in time. Before Gauss, mathematicians had wrestled with primes for centuries. They had proven foundational results and proposed conjectures. To understand how Gauss extended that tradition, it becomes necessary to examine what was already known and where the unanswered questions remained. Long before Carl Friedrich Gauss began counting primes in Brunswick, mathematicians had already spent more than 2,000 years thinking about them. The fascination did not begin in the 18th century. It began in antiquity, when numbers themselves were objects of philosophical inquiry as much as practical tools. In ancient Greece, arithmetic was not merely about commerce or measurement. It was tied to questions about harmony, proportion, and structure. The Pythagoreans regarded numbers as fundamental components of reality. While many of their ideas were mystical, they also studied divisibility and classification of numbers with seriousness. Within this framework, prime numbers quickly stood out. A prime number cannot be decomposed into smaller multiplicative parts. For Greek mathematicians, this indivisibility carried conceptual weight. Composite numbers could be broken apart. Primes resisted such reduction. That resistance made them significant. The earliest surviving systematic study of primes appears in the work of Euclid, particularly in Book 9 of Elements. Euclid provided the first known proof that there are infinitely many prime numbers. His argument is direct and remains elegant by modern standards. Assume there are only finitely many primes. List them: P1, P2, P3, up to Pn. Multiply them together and add 1. The resulting number cannot be divisible by any of the primes in the list because division would leave a remainder of 1. Therefore, either the new number is prime itself, or it has a prime factor not included in the original list. In either case, the assumption that the list was complete is false, hence primes are infinite. This proof did not describe where primes appear or how often. It established only that they never cease. Euclid also explored properties of perfect numbers, numbers equal to the sum of their proper divisors, and connected them to primes of a special form. His work demonstrated that primes were not isolated curiosities, but central to broader arithmetic structures. Centuries passed before significant progress resumed. After the decline of classical Greek mathematics, much of the work was preserved and transmitted through Islamic scholars, then reintroduced to Europe during the Middle Ages. By the Renaissance, arithmetic and algebra were expanding again. In the 17th century, interest in number theory intensified. Pierre de Fermat proposed numerous conjectures involving primes. He suggested that numbers of the form 2 to the power of 2 to the power of n plus 1 were prime, at least for small values of n. These are now called Fermat numbers. The first few are indeed prime, but later examples are composite. Fermat's bold conjectures stimulated further investigation. Fermat also proposed what became known as Fermat's last theorem, involving integer solutions to equations of the form a to the power of n plus b to the power of n equals c to the power of n. Though not solely about primes, his work highlighted the complexity of relationships among integers and prime factors. Another key figure was Leonhard Euler in the 18th century. Euler extended Fermat's ideas and corrected several conjectures. He demonstrated that not all Fermat numbers are prime by factoring one of them. More importantly for the future of prime distribution, Euler established a connection between primes and infinite series. Euler considered the harmonic series 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth plus, and so on, and showed that it diverges. Then he expressed this series as a product over primes, revealing a profound identity: 1 plus 1 half plus 1 third plus 1 fourth plus ... equals product over primes of 1 over 1 minus 1 over p. This formula, now known as the Euler product formula for the Riemann zeta function, linked additive properties of numbers to multiplicative properties of primes. It demonstrated that primes are not just scattered integers, but structurally embedded in analytic expressions. Euler also proved that the sum of the reciprocals of primes diverges. Although primes become rarer as numbers grow, their scarcity is not sufficient to make that reciprocal sum converge. This result suggested that primes thin out slowly. Still, no one had formulated a precise asymptotic law for their distribution. Other mathematicians compiled prime tables. They verified primality through divisibility tests and recorded sequences up to increasingly large bounds. These tables served both practical and theoretical purposes. In the absence of computers, tables were indispensable tools. Adrien-Marie Legendre, working in the late 18th century, attempted to approximate the number of primes less than n using a formula involving n divided by the logarithm of n minus a constant. His approximation was empirically motivated. It was not proven rigorously, but it represented a step toward recognizing logarithmic behavior. Despite these advances, the ancient obsession with primes remained largely descriptive. Mathematicians could prove infinite existence. They could connect primes to analytic functions. They could propose approximations, but they lacked a definitive theorem describing prime density. The intellectual climate encouraged persistence. Number theory was valued for its depth and difficulty. Unlike geometry, which often dealt with visualizable shapes, number theory dealt with abstract relationships. It required reasoning detached from physical intuition. The problem of prime distribution stood at the intersection of arithmetic and analysis. Counting primes was arithmetic. Approximating counts with logarithms required analysis. By the time Gauss began examining prime tables as a teenager, he inherited centuries of partial understanding. He knew Euclid's proof of infinitude. He likely studied Euler's analytic methods. He was aware that primes thin out, but not precisely how. What distinguishes his contribution is not that he was the first to notice thinning. It is that he formulated a specific asymptotic expression. Pi of n is approximately equal to n divided by log of n. This was more than empirical curve fitting. It implied that prime density near n is about 1 divided by len n. That density decreases slowly enough to ensure infinite continuation, yet predictably enough to approximate counts. The ancient mathematicians did not possess the analytic framework required to express such a relationship clearly. Logarithms were unavailable in Euclid's time. Infinite series had not been formalized. Even Euler's work did not culminate in a statement equivalent to the Prime Number Theorem. Thus, the ancient obsession with primes created a foundation without solving the central distribution problem. There is also a philosophical dimension. Prime numbers are deterministic. Each number either has divisors or it does not. There is no randomness in their definition, yet their large-scale behavior resembles probabilistic systems. This duality, strict determinism producing statistical regularity, became clearer only with analytic tools developed in the Enlightenment. Earlier mathematicians sensed mystery, but lacked the means to articulate it quantitatively. Another reason primes captivated scholars is their resistance to pattern generation. Attempts to produce formulas generating only primes repeatedly failed. Polynomials sometimes generate primes for small inputs but inevitably yield composite numbers eventually. The absence of a simple formula heightened intrigue. Gauss entered this long tradition not as an outsider, but as an inheritor. He did not begin from ignorance of earlier results. He absorbed them and recognized their limitations. It is instructive to consider the gap between Euclid and Gauss. Over 2 millennia separated their work. Yet the fundamental question, how are primes distributed, remained unresolved. This persistence indicates both the depth of the problem and the incremental nature of mathematical progress. By the late 18th century, enough numerical data existed to suggest logarithmic behavior, but articulating that behavior required confidence in analytic approximation. It required comfort with the idea that an exact sequence might obey an asymptotic law. Gauss's conjecture bridged that gap. He did not solve the problem definitively, but he identified the correct form of the solution. Ancient mathematicians had established that primes are infinite and foundational. Enlightenment mathematicians had linked primes to analytic functions. Gauss synthesized these strands by focusing on cumulative density. The obsession with primes was no longer purely philosophical or descriptive. It was becoming quantitative. To see how this shift unfolded in practice, one must return to the teenage Gauss examining prime tables. What did he see when he counted? What patterns convinced him that logarithms were involved? And how did careful tabulation transform centuries of curiosity into a concrete approximation? By the time Carl Friedrich Gauss began studying prime numbers seriously, mathematicians had already tried for centuries to impose simple patterns on them. They had searched for regular spacing, algebraic formulas, geometric analogies, and mechanical rules. Each attempt produced partial insights, but no straightforward structure emerged. Prime numbers are defined by what they are not. A prime is not divisible by any smaller whole number except 1. That negative definition makes them resistant to positive description. Composite numbers can be described through multiplication. Primes resist decomposition. They simply stand alone. When one writes out the sequence of natural numbers and marks primes, the arrangement does not resemble a repeating cycle. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. The gaps between consecutive primes vary unpredictably. Between 2 and 3 the gap is 1. Between 3 and 5 it is 2. Between 7 and 11 it is 4. Later, larger gaps appear. Yet occasionally primes sit surprisingly close together, such as 101 and 103. Mathematicians hoped for some hidden periodicity. Perhaps primes followed a modular pattern. Perhaps after a certain threshold, spacing stabilized. But no such regularity held consistently. Even attempts to find formulas that generate only primes repeatedly failed. For example, the quadratic expression n squared plus n plus 41 produces prime numbers for n equals 0 through 39. At n equals 40, however, the result is 40 squared plus 40 plus 41 equals 1681, which equals 41 times 41 and is therefore composite. Promising patterns would persist for dozens of steps before breaking unexpectedly. This tendency to appear structured locally but fail globally frustrated mathematicians. The primes seem to tease order without committing to it. Another approach was geometric. Some thinkers imagined arranging numbers in spirals or grids to visualize prime distribution. Certain visual patterns appeared striking, with diagonal lines of primes forming in number spirals. Yet closer examination revealed that these patterns did not translate into simple predictive laws. By the 18th century, extensive prime tables existed. Mathematicians could examine primes up to tens of thousands. These tables made it clear that primes become less frequent as numbers grow. But how precisely does that thinning occur? At first, one might suspect a linear rule. Perhaps primes occur roughly every k numbers for large K. But as numbers increase, the average gap between primes grows. It does not stabilize at a constant value. Next, one might consider polynomial behavior. Could the average gap grow proportionally to n itself? That would imply primes vanish rapidly, which contradicts Euclid's proof of infinitude and the observed density even at large scales. The challenge lies in reconciling two observations. First, primes never stop. Second, they become increasingly rare. When Gauss examined prime tables as a teenager, he confronted this tension directly. The tables did not reveal an obvious repeating cycle. They did not suggest arithmetic progression. Instead, they displayed irregular clustering combined with gradual thinning. Consider counting primes within successive intervals of equal length. Between 1 and 100 there are 25 primes. Between 101 and 200 there are 21. Between 201 and 300 there are 16. Between 901 and 1000 there are 14. The counts decrease, but not smoothly. Such irregularity makes it difficult to detect pattern by simple inspection. Human intuition struggles with noisy data. Short intervals mislead. One region may contain an unexpectedly large cluster. Another may contain a long gap. If Gauss had focused only on local spacing, he might have concluded that primes are chaotic. Instead, he shifted perspective. Rather than examining individual gaps, he examined cumulative totals. He asked how many primes lie below n, not how far apart consecutive primes are. This shift smooths irregularities. Local fluctuations become less dominant when aggregated. Yet even cumulative counts do not yield a simple polynomial formula. The growth of pi of n, the prime counting function, is slower than linear but faster than logarithmic. It increases without bound, but at a decreasing rate relative to n. Early approximations attempted to capture this growth. Adrien-Marie Legendre proposed that pi of n is approximately equal to n divided by log of n minus a constant. His formula fit numerical data moderately well. However, it was based on empirical fitting rather than theoretical derivation. The fact that Legendre's approximation resembled Gauss's later conjecture suggests that multiple mathematicians were sensing logarithmic behavior. But recognizing logarithms does not automatically produce proof. Why logarithms? Because the natural logarithm grows slowly. For example, log of 10 is approximately 2.3 log of 100 is approximately 4.6 log, of 1000 is approximately 6.9, log of 1 million is approximately 13.8. As n increases by powers of 10, ln of n increases steadily but modestly. Dividing n by ln of n produces a quantity that increases almost linearly but slightly slower. This behaviour aligns closely with observed prime counts. However, nothing in the definition of primes mentions logarithms. The link arises from analytic reasoning. One heuristic argument considers the probability that a large number n is divisible by small primes. The probability that n is not divisible by 2 is about 1/2, not divisible by 3, about 2/3, not divisible by 5, about 4/5. Multiplying such factors together suggests that the chance a number survives all small divisibility tests declines, roughly like 1 over the natural logarithm of n. This reasoning is subtle and not entirely rigorous, especially when first formulated. It involves approximations and assumptions about independence of divisibility conditions. Nonetheless, it hints at why logarithms appear naturally. Still, from the perspective of someone staring at tables, the pattern does not announce itself clearly. If Gauss examined primes below 10,000, he would see clusters and gaps. He would need to calculate ratios carefully to notice convergence toward n over natural log of n. The difficulty lies in scale. For small n, approximations are rough. Only as n grows large does the ratio pi of n divided by n over the natural logarithm of n approach one more closely. Without extensive data, the trend remains obscured by irregularity. In the 18th century, computing pi of n for very large n required manual verification. Errors were possible, tables were limited. Recognizing asymptotic behavior demanded both computational persistence and theoretical intuition. Patterns refused to appear in the sense that no simple arithmetic law governed prime spacing. There was no formula like every kth number is prime after a certain point. Instead, primes followed a statistical distribution embedded in analytic structure. This refusal of simple pattern distinguishes primes from many other mathematical sequences. Even the Fibonacci sequence, though recursive, has clear generation rules. Primes resist such recursion in elementary terms. Gauss's approach circumvented the need for explicit generation. He did not attempt to predict the next prime directly. He attempted to approximate how many primes exist up to a given boundary. That change in question reframes the entire problem. Instead of seeking exact positions, one seeks density. It is important to emphasize that density does not eliminate irregularity. Even if pi of n approximates n over ln of n, individual gaps remain unpredictable. Large gaps occur, twin primes appear, local behavior remains complex. This duality, global order, local irregularity, makes prime numbers both frustrating and compelling. At 15, Gauss recognized that the absence of simple spacing did not imply absence of law. He accepted that primes might not form an arithmetic progression. Instead, he sought a smooth curve approximating their cumulative count. That insight required intellectual flexibility. Many earlier mathematicians had focused on explicit formulas for generating primes. Gauss shifted attention to asymptotic approximation. In modern language, he anticipated analytic number theory. He treated primes not merely as arithmetic objects, but as entities whose distribution can be studied through continuous functions. Patterns refused to appear when approached from the wrong angle. Viewed through the lens of cumulative growth and logarithmic scaling, structure emerged. The next step in this development involved concrete computation. How exactly did Gauss examine prime tables? What numbers did he calculate? How did he test his approximation? Understanding the practical process clarifies how a teenager transformed centuries of frustration into a credible conjecture. By the time Carl Friedrich Gauss reached his mid-teens, he was no longer working through elementary arithmetic exercises. He had moved well beyond classroom drills and into independent study. Yet the object in front of him was not a sophisticated machine or a complicated geometric diagram. It was a table of numbers. Prime tables in the 18th century were compiled painstakingly. Each entry required verification through divisibility checks. There were no electronic calculators, no automated sieves running in milliseconds. If a mathematician wanted to know which numbers below 10,000 were prime, someone had to test each candidate. One common method for generating primes was a version of the sieve of Eratosthenes, an ancient algorithm. You begin by listing integers in order. Starting with 2, you eliminate all multiples of 2, then move to 3 and eliminate multiples of 3. Continue with 5, 7, 11, and so on. The remaining numbers are primes. In practice, this method required careful bookkeeping to avoid errors. By Gauss's time, printed tables of primes were available for moderately large ranges. These tables did not interpret the primes. They simply recorded them. Imagine a young student examining such a list, column after column of numbers, 2, 3, 5, 7, 11, 13, 17, continuing into the hundreds and thousands. At first glance, the sequence appears irregular. No repeating cycle, no obvious rule. A casual reader might scan the list and move on. Gauss did something different. He counted. Instead of focusing on where the next prime might appear, he focused on how many had appeared so far. For each threshold, 100, 200, 500, 1000, he tallied the total number of primes below that boundary. Let us reconstruct what he might have observed using known values. Below 10, 4 primes. Below 100, 25 primes. Below 1000, 168 primes. Below 10,000, 1,229 primes. These numbers grow steadily, but not proportionally to the boundary itself. If primes occurred with fixed density, pi of n would be proportional to n. But the ratio pi of n over n decreases as n increases. Gauss likely computed such ratios explicitly. For n equals 100, pi of n over n equals 25 hundredths, or 0.25. For n equals 1000, it equals 168 over 1000, or 0.168. For n equals 10,000, it equals 1229 over 10,000, or approximately 0.123. The density decreases, but not abruptly. The decline is gradual. Next, he may have compared n to pi of n directly. For n equals 1000, dividing 1000 by 168 gives approximately 5.95. For n equals 10,000, dividing 10,000 by 1,229 gives about 8.14. The quotient increases slowly. What kind of function grows slowly and steadily like this? Linear growth is too fast. Square roots grow more slowly than linearly, but their behavior does not align numerically with the observed ratios. Logarithms, however, increase at a rate that mirrors this gradual change. The natural logarithm of 100 is about 4.6. For 1000, it is about 6.9. For 10,000, about 9.2. These values are close to the ratios n over pi of n computed above, though not identical. The resemblance would not escape someone skilled in analysis. It is one thing to notice similarity, it is another to formalize it. Gauss began suspecting that pi of n is approximately n divided by log base e of n. He recorded this idea in his mathematical diary around 1792 or 1793, when he was about 15 years old. His diary entry was brief. It did not include an elaborate derivation. It stated essentially that the density of primes near n behaves like 1 over the natural logarithm of n. The simplicity of the statement belies the depth of observation behind it. To appreciate the difficulty of reaching such a conjecture, consider the absence of modern visualization tools. Today one could plot pi of n and n over ln of n on a graph, and see the curves align. Gauss had to rely on manual computation and comparison. He also had to trust that irregular fluctuations at smaller scales would smooth out at larger ones. This requires confidence in asymptotic reasoning, the idea that behavior becomes clearer as numbers grow. As a teenager, he was already comfortable with advanced mathematical ideas. He studied logarithms not merely as computational aids but as analytic functions. He understood that ln of n increases without bound but does so slowly. Dividing n by ln n produces a curve that increases almost linearly, but with slight deceleration, matching prime counts remarkably well. Yet he did not claim exact equality. He recognized that pi of n is not precisely n over natural log of n. Instead, it approaches that value asymptotically. This distinction is subtle and crucial. It reflects maturity in mathematical thinking. Why did he not publish immediately? Several reasons are plausible. First, he lacked a rigorous proof. Conjecture without proof held limited weight in formal mathematics. Second, he was still a student, developing broader expertise. Third, his personality inclined him toward caution. Gauss's reluctance to publish prematurely became a recurring theme in his career. He often preferred to withhold ideas until fully established. In the case of prime distribution, he sensed correctness, but could not yet demonstrate it rigorously. Nevertheless, the conjecture existed in his notes. It would later become known as the Prime Number Theorem, though the proof would not arrive until the end of the 19th century. The act of counting primes and comparing them to logarithms might seem methodical rather than inspired, but the conceptual shift involved was significant. Many mathematicians before him had tabulated primes. Few had thought to compare cumulative counts systematically with analytic functions. Gauss's curiosity was not satisfied by listing primes. He wanted to understand their behavior at scale. This approach reveals an important trait. He treated empirical data as guidance rather than as an endpoint. The table of primes was not a final result. It was evidence pointing toward a deeper law. Another aspect of his teenage work deserves attention. He did not limit himself to small ranges. Evidence suggests he examined primes up to several thousand at least. Extending tables increases reliability of approximation. Local irregularities become less influential in large data sets. By calculating pi of n for larger n, he strengthened his confidence that the ratio pi of n divided by n over ln of n approaches 1 gradually. Even if small values deviated significantly, the trend became clearer as n increased. One might imagine him recalculating values repeatedly, checking arithmetic, refining approximations. Errors in early tables could mislead conclusions. Precision mattered. At 15, such sustained engagement with abstract data indicates more than raw intelligence. It indicates persistence. He was not working toward external reward. There was no immediate prize for approximating prime density. The motivation appears internal, a desire to resolve apparent irregularity into structured understanding. The broader mathematical community would take decades to catch up fully. Adrien-Marie Legendre proposed a similar approximation independently. Later, in 1896, Jacques Hadamard and Charles-Jean de la Vallée-Poussin proved the prime number theorem rigorously using complex analysis and properties of the Riemann zeta function. But long before those proofs, the essential pattern had been recognized in a notebook belonging to a teenager studying prime tables. The scene remained simple: a table of numbers, columns of primes, ratios scribbled in margins, logarithms calculated carefully. No public announcement, no formal lecture, just careful observation leading to conjecture. Understanding this moment clarifies why the distribution of primes is not accidental. It follows a law discoverable through disciplined analysis. The next question, then, is how Gauss refined this insight. What convinced him that logarithmic behavior was not coincidence but necessity? And how did his growing mathematical education support the conjecture he had already sketched in youth? When Carl Friedrich Gauss began counting primes, He was confronting a paradox that had unsettled mathematicians for centuries. Euclid had already proven that prime numbers never end. There is no largest prime, no final entry in the sequence, yet infinity, while conceptually powerful, offers little practical guidance. To say that primes are infinite does not answer how many appear below 1 million, or 1 billion, or any other specific boundary. Infinity guarantees continuation, not distribution. The act of counting primes below a given number may appear straightforward at first. In principle, one lists numbers from 2 upward and checks divisibility. Each confirmed prime increases the tally, but the difficulty escalates rapidly. Verifying primes below 100 is manageable. Below 1,000 requires sustained effort. Below 10,000 becomes laborious. Beyond that, the task becomes increasingly demanding without mechanical assistance. Gauss was not attempting to list every prime individually for its own sake. He was asking a different question. How does the count of primes grow as numbers increase? He was attempting to quantify a trend. To formalize this question, mathematicians use the function pi of n, which represents the number of primes less than or equal to n. For small values, pi of n can be computed directly. For example, pi of 10 equals 4, pi of 100 equals 25 pi of 1000, equals 168 pi of 10,000, equals 1229. Each increase in n produces an increase in pi of n, but the growth is not proportional to n itself. The ratio pi of n over n decreases steadily. This observation raises a natural question. Can pi of n be expressed approximately in terms of n? At first, one might attempt a linear approximation. Suppose pi of n is roughly equal to n divided by some constant. That would imply primes maintain a fixed density. But empirical counts contradict this. The density decreases. Next, consider square root behavior. Perhaps pi of n grows proportionally to the square root of n. But that would imply extremely slow growth relative to n, far slower than observed data supports. Gauss's attention turned toward logarithms. The natural logarithm function grows steadily but slowly. Its behavior matches the gradual thinning of primes. Consider the comparison numerically. For n equals 100, log base e of 100 is approximately 4.605. N over log base e of n is approximately 21.7. The actual value of pi of 100 is 25. For n equals 1000, log base e of 1000 is approximately 6.907. N over ln of n approximately 144.8. The actual pi of 1000 is 168. For n equals 10,000, ln of 10,000 approximately 9.210. N over ln of n approximately 1085. The actual pi of 10,000 is 1229. The approximation underestimates the true count for these moderate values, but the trend becomes more accurate as n increases. The ratio pi of n divided by n over ln of n moves closer to 1 for larger n. This behavior suggests asymptotic equivalence. As n grows without bound, pi of n approaches n over log base e of n in relative terms. To appreciate the intellectual challenge here, remember that Gauss did not possess the modern notation of asymptotics. The formal language of limits and convergence was still evolving, yet he understood the essential idea. Exact equality is unnecessary. Trend alignment suffices. Counting primes manually was tedious, but counting them allowed detection of pattern invisible to casual inspection. Imagine him extending tables. For each 1,000 numbers, he would record how many primes appeared. He would then compare these counts with n over ln n. Differences would appear, but relative error would decrease gradually. The phrase, counting the uncountable, reflects the tension. Primes are infinite. One cannot count them all. Yet one can count how many lie below any finite boundary. The infinite sequence becomes manageable in segments. Gauss's approach required comfort with both infinity and finitude. Infinity guarantees that pi of n increases without bound. Finite computation reveals the rate of increase. Another subtlety arises in comparing pi of n with n over log base e of n. The function n over ln of n is continuous and smooth. Pi of n increases in discrete steps. It jumps by 1 at each prime and remains constant at composite numbers. The two functions differ in nature, one continuous, one stepwise. Yet their overall growth curves align closely for large n. Recognizing this alignment requires abstraction. One must be willing to compare a discrete function with a continuous one. This conceptual leap foreshadows analytic number theory, where such comparisons are routine. Gauss's diary entry did not include a proof. It likely reflected numerical evidence combined with theoretical intuition. He may have reasoned heuristically about divisibility probabilities. Consider a heuristic argument that might have influenced him. The probability that a large integer n is divisible by 2 is 1/2. The probability that it is divisible by 3 is 1/3. To be prime, n must avoid divisibility by 2, 3, 5, 7, and all smaller primes up to the square root of n. If one approximates the probability that n survives all such divisibility tests by multiplying factors like 1 minus 1 over p for primes p less than or equal to the square root of n, one eventually reaches an expression involving logarithms. While not rigorous in early form, this reasoning suggests density roughly proportional to 1 over natural log of n. Whether Gauss explicitly formulated this probabilistic argument at 15 is uncertain. What is clear is that he saw logarithmic behavior in data. Counting primes required meticulous arithmetic. Errors could distort conclusions. Tables had to be trusted or verified. The discipline required for such counting at a young age reflects his broader method. He did not rely solely on theoretical elegance. He grounded intuition in computation. There is another dimension to this work. By focusing on p of n, Gauss was reframing prime numbers as a collective phenomenon rather than individual curiosities. Instead of asking about the next prime, he asked about aggregate behavior. This shift mirrors developments in other scientific fields. In astronomy, astronomers moved from describing individual stars to understanding galactic structure. In physics, researchers moved from analysing single collisions to studying statistical mechanics of large systems. Gauss applied similar thinking within arithmetic. The phrase law of primes might suggest strict determinism. In reality, the law he sensed was asymptotic. It described average density, not precise position. The distinction matters. Even if pi of n approximates n over ln of n, there will always be irregularities. Some intervals contain more primes than expected, others fewer. But over large scales, deviations average out. The eventual proof of the prime number theorem in 1896 relied on complex analysis and properties of the Riemann zeta function. Jacques Hadamard and Charles Jean de la Vallée-Poussin independently demonstrated that pi of n is approximately n over ln of n as n approaches infinity. Gauss did not possess those analytic tools at 15. He possessed insight and persistence. Counting primes below 10,000 or beyond by hand might appear monotonous. Yet within that monotony lies pattern detection. The table of numbers was not random noise. It encoded a smooth curve obscured by stepwise jumps. Recognizing that curve required seeing beyond individual entries, this raises an important question. Once Gauss suspected the logarithmic law, how confident was he? Did he test additional ranges? Did he attempt refinements? Later correspondence suggests he believed the logarithmic integral function provided an even better approximation than n over ln of n alone. The logarithmic integral, denoted li of n, refines the estimate and aligns even more closely with pi of n for large values. Gauss later advocated this improved approximation. The evolution from n over ln of n to li of n reflects deeper engagement with analysis. But the essential recognition remained. Prime density is governed by logarithmic behavior. Counting the uncountable did not mean enumerating infinity. It meant understanding growth rate. This perspective would shape analytic number theory for generations. The teenage conjecture became a guiding principle for later research. With this approximation in mind, the next step is to examine the moment of articulation. How did Gauss record his insight? What form did it take in his notes? And how did that private entry influence the mathematical developments that followed decades later? Sometime around 1792 or 1793, when Carl Friedrich Gauss was about 15 years old, he wrote a short entry in what would later be known as his mathematical diary. The notebook itself was modest. It did not contain lengthy explanations or polished arguments. Instead, it recorded results, brief statements of discovery, often without proof, sometimes only a line long. Many of those lines would later correspond to major developments in mathematics. Among them was an observation about prime numbers. Gauss noted that the density of primes near a large number n appears to be approximately 1 divided by the natural logarithm of n. In modern notation, this implies that the number of primes less than n, denoted pi of n, behaves approximately like n divided by log base e of n. The statement was compact. It did not include tables or elaborate calculations. But behind that single line stood years of accumulated mathematical culture and careful counting. To understand why this was remarkable, it helps to consider what the statement actually means. If pi of n is approximately n over ln of n, then for very large n, the ratio pi of n divided by n over ln of n approaches 1. In other words, n over ln of n becomes an increasingly accurate estimate for the number of primes below n as n grows. This is not a guess about a small interval. It is a claim about the asymptotic structure of the entire number system. At 15, Gauss was not simply observing that primes thin out. That had been known informally for centuries. He was proposing the correct rate at which they thin out. There are infinitely many possible ways a sequence could become sparser. It could decrease proportionally to 1 over n. It could decrease exponentially. It could follow square root behavior. That primes follow logarithmic thinning is highly specific. Why logarithms? The natural logarithm function grows without bound, but very slowly. For example, increasing n from 1000 to 1 million multiplies n by 1000. Yet log base n of n increases only from about 6.9 to about 13.8. Dividing n by log base n of n therefore produces a function that increases almost linearly, but slightly slower. Empirical data align closely with this curve, but recognizing that alignment requires abstraction. Gauss's insight was not derived from a formal limit calculation. The rigorous concept of limits and asymptotic equivalence was still being refined at the time. Instead, he relied on pattern recognition grounded in calculation. It is important to avoid imagining a sudden flash of inspiration detached from evidence. He likely computed values of pi of n for increasing n and compared them to n over n of n. The resemblance would have been clear enough to justify conjecture. What makes the insight remarkable is not just its correctness, but its timing. The prime number theorem, the formal statement that P of n is approximately n over ln of n, would not be proven until 1896, more than a century later, by Jacques Hadamard and Charles-Jean de la Vallée-Poussin. Their proofs relied on complex analysis and properties of the Riemann zeta function, mathematical tools unavailable in Gauss's youth. Yet the essential form of the theorem was already present in his diary. There is another subtle aspect of his insight. Gauss later suggested that an even better approximation for pi of n is given by the logarithmic integral function, denoted L of n. The logarithmic integral grows slightly faster than n over n and matches actual prime counts more closely for large n. The logarithmic integral is defined as the integral from 2 to n of dt divided by ln(t). This expression refines the approximation by accounting for gradual variation in logarithmic density. The fact that Gauss moved beyond n over ln n to Li(n) demonstrates depth of understanding. He was not satisfied with a rough estimate. He sought improved alignment with data. At 15, however, the initial observation that logarithmic behaviour governs prime density was already extraordinary. To appreciate its difficulty, consider what he did not know. He did not have access to the Riemann hypothesis, proposed decades later by Bernhard Riemann, which connects zeros of the zeta function to fluctuations in prime distribution. He did not possess complex contour integration techniques used in later proofs. He did not rely on formal analytic continuation. He relied on data analytic intuition. The diary entry itself was private. Gauss did not publish it immediately. His reluctance to share unproven conjectures was consistent throughout his career. He preferred certainty. This caution sometimes meant that others independently rediscovered ideas he had already formulated. In the case of prime distribution, Adrien-Marie Legendre proposed a similar approximation in published work. The degree to which Legendre was influenced by Gauss's earlier ideas remains debated, but the essential insight had already been recorded by Gauss years before. There is a broader lesson in this moment. Mathematical discovery does not always proceed through formal proof first. Often conjecture precedes demonstration. Recognizing pattern comes before establishing necessity. Gauss's remark about prime density was a conjecture grounded in evidence. It required later generations to provide proof. The idea also illustrates a shift in perspective. Rather than treating prime numbers as isolated objects, he treated them as a statistical ensemble. He examined global behavior rather than local irregularity. This shift mirrors developments in other sciences during the Enlightenment and beyond. Physicists learned to describe gas behavior statistically rather than tracking individual molecules. Astronomers described star populations rather than individual stars. Gauss applied similar reasoning to arithmetic. Another aspect of the insight is its simplicity. The formula pi of n is approximately n over log base e of n is concise. Its elegance conceals the complexity of the phenomenon it describes. One might ask why primes, defined purely through divisibility, should relate to logarithms, functions that arise from continuous growth processes. The connection emerges from deep properties of multiplicative structure and analytic continuation. But Gauss did not need full theoretical machinery to suspect the relationship. His intuition anticipated analytic number theory before the field was formally established. It is also worth noting that his conjecture did not eliminate unpredictability. Individual primes remain irregular. Large gaps occur. Twin primes persist. The law describes average density, not exact positions. This distinction is crucial. The law of primes is not a simple generating rule. It is an asymptotic description. Gauss understood that distinction implicitly. His diary entry did not claim precise equality. It suggested approximation. The remarkable nature of this insight lies in its foresight. He recognized a deep structural property of the number system before analytic tools made proof feasible. As he matured, Gauss would become known as the Prince of Mathematicians. His contributions spanned geometry, astronomy, magnetism, statistics, and complex analysis. Yet the teenage conjecture about prime density stands as one of his earliest profound insights. The notebook entry was brief, but its implications were vast. It indicated that prime numbers, though individually erratic, collectively obey a smooth mathematical law. The next question is why he chose not to publish this conjecture immediately, and how his characteristic caution shaped the trajectory of number theory in the decades that followed. When Carl Friedrich Gauss wrote in his mathematical diary that the density of primes near a large number n and n behaves like 1 over the natural logarithm of n, 1 over the natural logarithm of n, he was not drafting a paper for publication. He was recording a private conclusion. That distinction matters. The idea that would later become known as the Prime Number Theorem began not as a public announcement, but as a restrained observation written for himself. Gauss kept his mathematical diary from 1796 onward, though earlier notes and calculations shaped its entries. The diary was not expansive. It contained short statements, compressed results without explanation. Often he omitted derivations entirely. The tone was factual, almost terse. The entry concerning prime distribution fits that pattern. It did not argue, it did not persuade, it simply stated what he believed to be true. Why did he not publish the conjecture? Part of the answer lies in temperament. Gauss had a well-documented reluctance to release ideas before he considered them fully proven. He disliked speculative claims without rigorous foundation. This caution shaped his entire career. He frequently discovered results years before others, but delayed publication until he could support them conclusively. In the case of prime distribution, he had strong numerical evidence but no proof. The approximation pi, n, approximately equals n over log n, pi, n, approximately equals n over log n, matched data convincingly for growing values of nn, yet it remained empirical. To publish it as a theorem would have required a demonstration he did not yet possess. It is important to understand the standards of mathematics at the time. By the late 18th century, rigor was becoming central. Calculus had been introduced in the previous century, but its foundations were still being clarified. Mathematical arguments were expected to meet high standards of logical coherence. Conjectures were common, but proofs carried authority. Gauss preferred certainty. Another factor may have been strategic focus. During his late teens and early 20s, Gauss was producing groundbreaking work in multiple areas. In 1796, he proved the constructibility of the regular 17 gon using only compass and straightedge, a major achievement in classical geometry. He worked on number theory more broadly, developing results that would later appear in his book Disquisitiones Arithmeticae, published in 1801. That book established him as a leading mathematician at a young age. Within that broader context, the conjecture about prime distribution may have seemed incomplete. It was an observation pointing toward a deeper theory not yet available. Publishing an unproven approximation might have distracted from work he could fully justify. Yet Gauss did not abandon the idea. Decades later, in correspondence with colleagues, he returned to the question. In letters written in 1849 and 1850, he explained that he had long believed the logarithmic integral provided the best approximation for pi, n pi n. He described how he had reached this conclusion based on numerical evidence many years earlier. By then, the conjecture was no longer merely a private note. It had become part of ongoing discussion among mathematicians. But the proof remained elusive. Meanwhile, other mathematicians approached similar approximations independently. Adrien-Marie Legendre proposed a formula for pi n involving n over ln n minus b, n over ln n minus b, where bb was a constant he estimated numerically. Legendre's work appeared in print. It did not cite Gauss's earlier diary entry, which was not publicly available. Whether Legendre derived his formula independently or was influenced indirectly through correspondence remains a subject of historical debate. What is clear is that the logarithmic relationship was beginning to circulate more widely. Gauss's silence illustrates an interesting dynamic in mathematics. Discovery does not always align with publication. Some insights remain private for years. When eventually revealed, they reshape understanding retroactively. Had Gauss published his conjecture in the 1790s, the history of number theory might have unfolded differently. Perhaps efforts toward proof would have accelerated. Perhaps analytic tools would have developed sooner. Or perhaps the conjecture would have remained unproven regardless, awaiting advances in complex analysis. It is also worth noting that Gauss's conjecture about primes was not his only unpublished insight. In several areas, including non-Euclidean geometry, he developed ideas ahead of his contemporaries but chose not to publish. In geometry, His reluctance allowed others such as Nikolai Lobachevsky and Janos Bolyai to take public credit for similar developments. In prime distribution, the eventual proof arrived long after his lifetime. His caution reflects both strength and limitation. It preserved his reputation for rigour, yet it delayed dissemination of ideas. Returning to the formula itself, P, N, approximately equals N over ln, N, Pi, N, approximately equals N over ln, N, is deceptively simple. The difficulty lies not in stating it, but in proving it. The eventual proof in 1896 by Jacques Hadamard and Charles-Jean de la Vallée-Poussin relied on properties of the Riemann zeta function, and the absence of zeros on a specific vertical line in the complex plane. These techniques belong to complex analysis, a field that matured only in the 19th century. Gauss, though later a pioneer in complex analysis, did not yet have access to the necessary theoretical apparatus at 15. His insight preceded the tools required for proof. There is something instructive in this sequence. Observation came first, proof followed a century later. The structure of mathematics allowed conjecture to exist independently of demonstration, provided evidence supported it. Gauss's private formulation therefore served as a bridge between empirical counting and analytic proof. The reluctance to publish also emphasizes his internal standards. He was not seeking recognition for bold claims. He valued internal coherence and certainty over visibility. In modern scientific culture, where rapid publication is often incentivized, this attitude appears unusual. In Gauss's era, it was part of his identity. The formula he did not publish eventually became central to analytic number theory. It guided research into error terms, the difference between pi, n, and n over s n. It motivated investigation into zeros of the zeta function, leading to Riemann's 1859 paper that introduced the Riemann hypothesis. In that sense, the diary entry was not an isolated remark. It was a seed from which entire branches of mathematics grew. Understanding why Gauss withheld publication clarifies the nature of his contribution. He was not hesitant because he doubted the pattern. He was hesitant because he demanded proof. His caution preserved intellectual integrity but delayed public awareness. The formula itself endured. It resurfaced in letters. It appeared implicitly in Legendre's approximation. It eventually became the formal statement of the Prime Number Theorem. The story now shifts from the act of withholding to the mathematical substance itself. If pi, n, behaves like n over ln, n over ln, n, why do logarithms arise at all? What deeper structure links divisibility of integers to continuous analytic functions? To answer that requires examining the unexpected bridge between primes and logarithms. At first glance, nothing about prime numbers suggests logarithms. A prime is defined through divisibility. A whole number greater than 1 that has no positive divisors other than 1 and itself. Logarithms, by contrast, arise from questions about exponential growth. They answer problems like, to what power must a base be raised to produce a given number? The two concepts seem unrelated. Yet in his teenage investigation, Carl Friedrich Gauss concluded that the density of primes near a large number nn behaves roughly like 1 over the natural logarithm of n, 1 over the natural logarithm of n. That claim implies a structural connection between multiplicative properties of integers and continuous analytic functions. Understanding this connection requires stepping back from individual primes and examining how divisibility interacts across the entire number line. Every composite number can be factored into primes. That means primes are responsible for the multiplicative structure of integers. When we ask whether a number is prime, we are asking whether it avoids divisibility by all smaller primes. In other words, prime distribution is controlled by how often numbers escape being divisible. Now consider a large integer nn. The probability that nn is divisible by 2 is approximately 1/2. Roughly half of all integers are even. The probability that nn is divisible by 3 is about 1/3, 1/3. About 1/3 of integers are multiples of 3. For 5, the fraction is 1/5, 1/5, and so on. To be prime, a number must avoid divisibility by 2, 3, 5, 7, 11, and all other primes less than or equal to nn. If one attempts a rough heuristic argument, one might multiply together the probability of avoiding divisibility by each prime, 1 minus 1/2, 1 minus 1/3, 1 minus 1/5, 1 minus 1/7, 1 minus 1/2, 1 minus 1/3, 1 minus 1/5, 1 minus 1/7. This product continues over primes up to nn. Although this reasoning assumes a kind of independence that is not strictly true, it produces a striking approximation. As this product extends over more primes, its value shrinks roughly in proportion to 1 over the natural logarithm of n, 1 over the natural logarithm of n. This heuristic connection between multiplicative factors and logarithmic decay is not accidental. It reflects a deeper analytic structure first revealed clearly by Leonhard Euler. Euler demonstrated that the harmonic series 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus ... 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus ... can be expressed as an infinite product over primes, product of p1 1 minus 1 over pp, product 1 minus 1 over p1. This identity links additive behavior, sums over integers, with multiplicative structure, products over primes. It shows that primes encode the structure of integers in a fundamental way. The logarithm enters naturally when analysing products. Taking the logarithm of a product converts it into a sum. For example, ln of pip of 1 minus 1 over p minus 1 equals sum of p minus ln of 1 minus 1, over p ln of p pi of 1 minus 1 over p minus 1 equals p sum of minus ln of 1 minus 1 over p. For small values of 1 over p1 over p, the logarithm can be approximated using a Taylor expansion, ln of 1 minus x, approximately minus x for small x. ln 1 minus x approximately equals minus x for small x. Applying this to x equals 1 over px equals 1 over p, we find minus ln 1 minus 1 over p approximately equals 1 over p. Minus ln 1 minus 1 over p approximately equals 1 over p. This suggests that the sum of reciprocals of primes influences the growth of logarithmic expressions. In fact, Euler proved that the sum of reciprocals of primes diverges, though more slowly than the harmonic series over all integers. This slow divergence is directly related to logarithmic growth. By the time Gauss examined prime tables, logarithms were well established as analytic tools. John Napier had introduced them in the early 17th century to simplify multiplication and division. By the 18th century, logarithmic tables were standard computational aids, but their deeper analytic significance was still unfolding. The natural logarithm function, ln of nln of n, measures cumulative growth in a specific way. It arises naturally when integrating 1 over x 1 over x. Indeed, integral 1 n 1x dx equals ln of n, integral 1 nx 1 dx equals ln of n. This integral connection is important because the density of primes behaves roughly like 1 over ln of n 1 over ln of n. In other words, prime frequency resembles the reciprocal of the cumulative growth of 1 over x 1 over x. Later developments in number theory would formalize this relationship using the Riemann zeta function, introduced by Bernhard Riemann in 1859. The zeta function encodes information about primes through its Euler product representation. Zeta of s equals product of p to the power of 1 over 1 minus p to the power of minus s. Zeta of s equals p product of 1 minus p to the power of minus s1. Zeros of this function govern fluctuations in prime distribution, but Gauss did not possess this framework when he made his conjecture. He worked from numerical evidence and analytic intuition, Still, the connection between logarithms and primes can be understood conceptually, even without advanced complex analysis. Suppose we ask, how many primes lie near a large number n? If the density at n is approximately 1 over the natural logarithm of n 1 over the natural logarithm of n, then the number of primes in a small interval of width dn around nn should be roughly dn over the natural logarithm of n dn over the natural logarithm of n. Integrating this density from 2 up to nn produces an approximation for pi, n, pi, n. That integral from 2n dt ln t integral from 2n ln t dtc is called the logarithmic integral function, often denoted li, n, l, n. Gauss later advocated this as an even more accurate approximation than n over ln, n over ln, n. The fact that integrating 1 over ln t 1 over ln t edus gives a strong estimate for prime counts reinforces the idea that prime density behaves smoothly on large scales. What makes this remarkable is that the definition of a prime involves only divisibility, yet its large-scale distribution follows a law expressible through continuous analysis. Discrete arithmetic gives rise to smooth analytic behaviour. This interplay between discrete and continuous mathematics became one of the defining features of 19th century analytic number theory. For Gauss as a teenager, the recognition of logarithmic thinning likely came from comparing ratios rather than from formal integration. He saw that dividing nn by ln, n ln n, tracked pi, n, pln n closely. That was enough to suggest underlying structure. There's also a conceptual reason logarithms appear. The average gap between consecutive primes near n and n is approximately ln, n, ln, n. That means primes become spaced roughly logarithmically farther apart as numbers increase. Since the average spacing grows like natural logarithm of n natural logarithm of n, the density, the reciprocal of spacing, must decrease like 1 over natural logarithm of n. This relationship between spacing and density clarifies the pattern. If primes near 1 million are about 14 numbers apart on average, and log base e of 1 million is approximately 13.8 log base e of 1 million is approximately 13.8, the alignment is evident. Thus, the logarithm is not an arbitrary function imposed externally. It emerges naturally from multiplicative structure and probabilistic reasoning about divisibility. The connection also reveals something deeper about mathematics itself. Simple definitions can lead to complex global behaviour. The condition divisible only by 1 in itself appears elementary, yet its consequences extend into complex analysis and asymptotic theory. Gauss's insight bridged elementary arithmetic and higher analysis decades before the formal tools were complete. The logarithm connection therefore represents more than a numerical coincidence. It marks the point where number theory became analytic. It suggests that primes, though discrete objects, obey laws describable by smooth functions. From this recognition emerged a new direction for mathematics, one that would require increasingly sophisticated methods to confirm fully. The next stage in the story involves seeing how Gauss refined his approximation, and how his quiet conjecture gradually transformed into a central theorem of number theory. Once Carl Friedrich Gauss had recognized that the density of primes near a large number n behaves roughly like 1 over the natural logarithm of n 1 over the natural logarithm of n, the question was no longer whether primes thin out. That much was evident. The deeper issue became how precisely this thinning could be described, and whether the approximation could be sharpened. The expression pi, n, approximately equals n over ln, n, pi, n, approximately equals n over ln, n, captures the essential trend. But when Gauss compared this estimate with actual prime counts, he would have noticed consistent deviation. For moderate values of n, the approximation underestimates the true count. The discrepancy narrows as n grows, but it remains measurable. This observation likely motivated refinement. Rather than relying solely on n over natural log of n, Gauss considered a more accurate function, the logarithmic integral. The logarithmic integral, written as Li n, equals integral 2 nd t ln t Li n equals integral 2 n ln t dt provides a closer approximation to pi n pi n for large n. Unlike the simpler formula, it accounts for the gradual change in density across the interval from 2 to n. In later correspondence, Gauss explained that he had long believed the logarithmic integral to be the correct guiding function. He described how comparisons with numerical tables convinced him of its accuracy. The fact that he revisited the idea decades after his initial conjecture suggests that he regarded it as more than a passing insight. To understand why the logarithmic integral improves the estimate, consider what the simpler approximation assumes. The expression n over ln, n over ln, n, effectively treats prime density as constant across the entire interval from 2 to n, equal to 1 over the natural logarithm of n, 1 over the natural logarithm of n. But in reality, the density changes gradually. Near smaller numbers, primes are more frequent. Near larger numbers, less so. Integrating 1 over the natural logarithm of t across the interval allows the density to vary continuously. This produces a curve that matches actual prime counts more closely. The difference between Li, n, and n over ln, n over ln, n is not enormous, but it becomes significant for precise estimation. Even so, both expressions share the same leading asymptotic behaviour. As n approaches infinity, the ratio pi n over ln n, pi n over ln n approaches 1. This asymptotic equivalence is the heart of what would later be called the prime number theorem. Yet during Gauss's youth, the theorem existed only as conjecture. No proof demonstrated that the ratio truly converges to 1. The numerical evidence was compelling but incomplete. Other mathematicians, including Adrien-Marie Legendre, proposed similar approximations independently. Legendre suggested a formula of the form Pias, n approximately equals nln, n minus b, Piase, n approximately equals ln, n minus bn, where bb was an empirically chosen constant. His expression improved accuracy for certain ranges, but like Gauss's approximation, it lacked rigorous proof. The convergence of multiple approximations toward logarithmic behaviour strengthened confidence that the pattern was genuine. Still, the law of primes did not yet have formal status. It existed as a strong empirical principle, supported by calculation and analytic reasoning, but unproven. At this stage, number theory was undergoing transformation. Arithmetic had long been concerned with exact properties of integers. Analysis, by contrast, dealt with continuous functions and limits. The emerging law of prime distribution required blending these perspectives. The difficulty lay in controlling error terms. Approximating Pias, n, with n over ln, n captures the leading trend, but how large can the difference Psi just past n minus n over ln has become? Does it fluctuate wildly? Does it remain bounded relative to n over ln, n over ln, n? These questions demanded tools beyond elementary arithmetic. The breakthrough came more than a century later, in 1896, when Jacques Hadamard and Charles-Jean de la Vallée-Poussin independently proved the prime number theorem. Their proofs relied on complex analysis and properties of the Riemann-Zeta function. The zeta function, introduced by Bernard Riemann in 1859, encodes information about primes through its Euler product representation. Riemann demonstrated that understanding the zeros of this function would illuminate prime distribution. Although he did not prove the prime number theorem, he outlined a path toward it. Hadamard and de la Vallée-Poussin showed that the zeta function has no zeros on the line in the complex plane, where the real part equals 1. This absence of zeros allowed them to control error terms and confirm that Pi's n is approximately n over ln. N, Pi, n, is approximately n over ln n. The fact that proof required complex analysis highlights how far ahead Gauss's intuition was. As a teenager, he did not possess this machinery. He identified the correct leading term decades before the analytic framework matured. The shaping of the law of primes therefore unfolded in stages. First came observation and counting, then came conjecture about logarithmic density. Later came refinement through the logarithmic integral. Finally came proof via complex analysis. Throughout this development, the core insight remained unchanged. Prime numbers, though irregular in detail, follow a smooth asymptotic law. It is instructive to consider what the theorem does not claim. It does not predict exact positions of primes. It does not eliminate large gaps. It does not resolve questions about twin primes or other specialized patterns. It describes average density. Even today, many open problems remain about primes. The Riemann hypothesis, concerning the precise location of zeros of the zeta function, remains unproven. It would provide sharper control over error terms in prime counting if resolved. Yet the leading law, Pi, n, approximately n over ln, n, pi, n, approximately n over ln, n, is firmly established. When Gauss first articulated his conjecture, none of this was certain. He had only tables and analytic reasoning, but he trusted the pattern he saw. There is a discipline in recognizing when data point toward a deeper rule. Gauss did not announce a bold theorem without proof. He recorded his observation privately, aware that full justification required more than numerical agreement. The law of primes took shape gradually. It began as a teenage conjecture. It matured through analytic refinement. It culminated in proof a century later. Understanding this progression reveals something about mathematical discovery. Laws are often sensed before they are proven. Evidence accumulates before theory solidifies. Gauss's early work stands at the beginning of this trajectory. His insight did not close the question, it opened a new direction. It reframed prime distribution as an analytic problem, rather than merely arithmetic. From that reframing, entire fields developed. The next aspect to examine is the personal dimension behind this intellectual patience. Why Gauss preferred silence and precision over premature announcement, and how that temperament shaped the pace at which the law of primes entered the mathematical world. One of the most striking aspects of Carl Friedrich Gauss is not only what he discovered, but how he chose to handle his discoveries. The conjecture about prime distribution did not appear in a published paper when he was 15. It did not circulate immediately through European academies. It remained in his private notes. This pattern, insight followed by restraint, would define much of his career. Gauss worked in an era when mathematics was becoming increasingly rigorous. Conjectures were common, but proof was the currency of permanence. He understood this deeply. For him, intuition was not enough. Numerical evidence was persuasive, but without demonstration it remained provisional. This attitude shaped his response to the pattern he observed in prime tables. He believed the density of primes followed a logarithmic law. He refined the approximation using the logarithmic integral. Yet he did not publish a bold claim declaring a theorem. He waited. The patience involved here should not be mistaken for hesitation born of doubt. Gauss often expressed strong confidence in his conclusions privately, but he demanded logical certainty before making them public. This habit appears repeatedly in his work. In geometry, he developed ideas that later became central to non-Euclidean geometry, yet he refrained from publishing them. In statistics, he formulated methods that would later be formalized as least squares estimation, but his presentation was cautious and grounded in application. In number theory, his Disquisitiones Arithmeticae displayed extraordinary depth, yet it avoided speculative claims. This pattern of silence reflects a specific philosophy of mathematics. Gauss valued internal coherence above public recognition. He preferred to construct results completely before unveiling them. Such discipline influenced the trajectory of the law of primes. Had Gauss published his conjecture in the 1790s, it might have shaped early 19th century research differently. Instead, the idea circulated slowly, re-emerging later through correspondence and independent approximation by others such as Adrien-Marie Legendre. Silence, in this case, did not suppress the idea permanently. It delayed its formal entry into mathematical discourse. There is also a methodological dimension. Prime distribution is subtle. Empirical agreement can mislead. Small ranges may suggest patterns that fail at larger scales. Gauss was aware of this risk. The numerical match between pi, n and n over ln, n over ln, n, improves as n grows, but for moderate values deviations remain visible. Without a framework capable of bounding those deviations, publishing a definitive claim would have been premature. Gauss recognized that the tools available in his youth were insufficient for rigorous proof. Patience allowed mathematics to mature around the conjecture. Precision also characterized his computational work. Counting primes below large values required careful verification. Errors in tables could distort ratios and undermine confidence. Gauss did not rely casually on approximate data. His numerical comparisons were deliberate. This precision extended beyond arithmetic into analytic reasoning. When he later discussed the logarithmic integral, he emphasized its closer fit compared to n over ln, n over ln, n. He did not settle for a rough estimate when refinement was possible. The temperament behind these choices reflects a broader intellectual culture. Late Enlightenment mathematics increasingly demanded clarity and rigor. Gauss absorbed this standard and elevated it. Yet silence carried consequences. In non-Euclidean geometry, his restraint allowed others to claim priority publicly. In prime distribution, his early conjecture did not become widely known until much later. The formal proof in 1896 by Jacques Hadamard and Charles-Jean de la Vallée-Poussin did not cite a widely disseminated teenage claim, though Gauss's letters revealed his earlier understanding. There is an interesting contrast between discovery and recognition. Gauss discovered patterns early. Recognition depended on publication. However, his silence did not diminish the depth of his insight. It preserved his internal standard. Mathematics must be demonstrated, not merely observed. Patience also allowed the field to evolve naturally. The eventual proof of the prime number theorem required complex analysis, particularly properties of the Riemann-Zeta function, introduced by Bernhard Riemann. These analytic tools were unavailable in Gauss's teenage years. Waiting allowed analytic number theory to develop the necessary structure. Precision shaped how the law of primes was eventually articulated. The theorem does not claim exact equality. It asserts asymptotic equivalence. As n approaches infinity, pi n behaves like n over ln n over ln n. This distinction is subtle and essential. Gauss's caution anticipated that subtlety. He did not claim primes are distributed exactly according to a simple formula. He recognized the approximation's asymptotic nature. This clarity prevented misunderstanding. The law describes global density, not local placement. Large prime gaps still occur, clusters still appear. The average spacing near nn grows roughly like ln, n, but individual intervals vary. Silence, patience, and precision together form a pattern in Gauss's character. He did not rush to attach his name to conjectures. He did not prioritize speed over certainty. He allowed ideas to mature internally. In modern terms, one might describe this as intellectual discipline. It reflects a commitment to standards rather than publicity. Understanding this personal dimension clarifies why the teenage discovery did not immediately transform mathematics. It also explains why later mathematicians sometimes rediscovered results Gauss had already found. Yet the law of primes continued to take shape beyond him. Legendre's approximation circulated. Riemann's zeta function introduced new analytic depth. By the late 19th century, the pieces were in place for proof. The narrative now moves forward in time. Decades after Gauss first recorded his conjecture, other mathematicians would independently approach similar approximations and eventually confirm the asymptotic law rigorously. To see how that unfolded requires examining how prime distribution resurfaced in later work and how the conjecture matured into theorem. When Carl Friedrich Gauss first recorded his conjecture about the density of prime numbers, he did so privately. He didn't publish a formal paper announcing that the number of primes below nn behaves like n over ln, n over ln, n. As a result, the mathematical world continued exploring prime distribution, largely unaware that a teenage Gauss had already identified the essential pattern. Decades passed. During the early 19th century, number theory was gaining structure and coherence. Gauss himself contributed significantly through his 1801 book Disquisitiones Arithmeticae, which established systematic foundations for modular arithmetic, quadratic reciprocity, and integer theory. However, that book did not contain a formal statement of the logarithmic law of primes. Meanwhile, mathematicians in France were independently studying prime distribution. Among them was Adrien-Marie Legendre. In 1798 and later editions of his work on number theory, Legendre proposed an empirical formula for the prime counting function, pi of n approximately n ln of n minus b, pi of n approximately ln of n minus bn, where bb was a constant he estimated numerically to be approximately 1.08366. Legendre's formula was based on careful comparison between calculated prime counts and logarithmic expressions. It differed slightly from Gauss's earlier formulation, but shared the same underlying principle. Prime density decreases in proportion to a logarithmic function. The resemblance between Legendre's approximation and Gauss's private conjecture is striking. Whether Legendre developed his idea independently or was influenced indirectly through correspondence remains debated. What is certain is that by the turn of the 19th century, the logarithmic pattern was emerging in multiple places. Still, Legendre did not provide a proof. His formula was empirical. It matched known data reasonably well, but it did not establish necessity. For several decades, prime distribution remained an open problem. Mathematicians refined tables, improved approximations, and explored related analytic expressions. The conjectured relationship between pi, n, and logarithms gained credibility, but lacked theoretical grounding. Then, in 1859, a new development reshaped the landscape. Bernhard Riemann published a short but profound paper titled On the Number of Primes Less Than a Given Magnitude. In this work, Riemann introduced the zeta function, defined initially for complex numbers with real part greater than 1. Zeta of s equals the sum from n equals 1 to infinity of 1 over n. Zeta of s equals n equals 1 sum from n to infinity ns1. He extended Euler's earlier product formula and demonstrated that the zeta function can be expressed as a product over primes. Zeta of s equals product of p11 minus p to the minus s. Zeta of s equals p pi 1 minus p to the power of minus s1. This identity revealed a deep connection between analytic functions and prime numbers. Riemann proposed that understanding the zeros of the zeta function would unlock precise control over prime distribution. In particular, he suggested that all non-trivial zeros lie on a critical line in the complex plane, a conjecture now known as the Riemann hypothesis. Although Riemann did not prove the prime number theorem, he provided a roadmap toward it. His analytic framework transformed prime distribution from an empirical observation into a question about complex analysis. By the late 19th century, analytic tools had matured sufficiently to address the problem directly. In 1896, two mathematicians working independently achieved the breakthrough, Jacques Hadamard and Charles Jean de la Vallée-Poussin. Both prove that the zeta function has no zeros on the line where the real part equals 1. This result allowed them to establish rigorously that pi of n is approximately n of n. P of n is approximately the natural logarithm of n. In other words, the ratio pi of n over the natural logarithm of n approaches 1 as n tends to infinity. The conjecture Gauss had written privately more than a century earlier was finally proven. It is important to note that Hadamard and de la Vallée-Poussin did not merely confirm a numerical pattern. They demonstrated that the logarithmic law follows necessarily from deep analytic properties of the zeta function. Their proofs were intricate, relying on complex variable theory, contour integration, and careful estimation of error terms. The rediscovery of the logarithmic pattern thus occurred in stages. Legendre proposed an empirical formula. Riemann connected primes to analytic continuation and complex zeros. Hadamard and de la Vallée-Poussin completed the proof. Throughout this process, the essential insight remained the same: primes thin out logarithmically. When Gauss later corresponded about prime distribution, he revealed that he had long believed in the logarithmic integral as the most accurate approximation. His earlier diary entry confirmed that he had recognized the pattern in youth. From a historical perspective, this sequence illustrates how mathematical ideas can emerge independently in different contexts. Empirical data suggested logarithmic behavior. Analytic reasoning confirmed it. The pieces converged. The rediscovery also underscores the difference between conjecture and theorem. For nearly a century, the logarithmic law existed as a strong belief supported by evidence. Only after analytic number theory matured could it be proven. This maturation required conceptual tools unavailable to Gauss at 15. Complex analysis, rigorous limit theory, and systematic study of infinite products developed gradually during the 19th century. Yet the seed of the idea lay in a table of numbers examined by a curious teenager in Brunswick. The story does not end with the proof of the prime number theorem. Questions remain about the size of the error term, the difference between pi, n, and its logarithmic approximation. The Riemann hypothesis, still unproven, would provide precise bounds on these fluctuations if resolved. Nevertheless, by 1896 the central law had been secured. The pattern others rediscovered and proved was the same one Gauss had sensed decades earlier. This convergence across generations highlights the continuity of mathematical investigation. A conjecture recorded privately can shape a century of research. Empirical observation can anticipate analytic necessity. The next stage in understanding the significance of this discovery lies in examining why prime distribution matters beyond pure arithmetic, and how this logarithmic law influences modern mathematics and technology. By the end of the 19th century, the conjecture that Carl Friedrich Gauss had quietly recorded as a teenager was no longer merely a pattern observed in tables. It had become a central target of analytic number theory. The claim that the number of primes less than a large number nn behaves like n over ln, n over ln, n had been tested extensively. Numerical evidence supported it. Heuristics justified it. But proof remained out of reach for decades. That changed in 1896. In that year, two mathematicians working independently, Jacques Hadamard in France and Charles Jean de la Vallée-Poussin in Belgium, proved what became known as the Prime Number Theorem. The theorem states that limit as n approaches infinity pi of n over n, natural log of n equals 1. N approaches infinity, limit n over natural log of n pi of n equals 1. In simpler terms, as numbers grow larger and larger, the ratio between the actual number of primes below n and the approximation n over natural log of n approaches 1. The approximation becomes increasingly accurate relative to the size of nn. To understand what Hadamard and de la Vallée-Poussin accomplished, it is necessary to examine the analytic framework that made the proof possible. The key lies in the Riemann zeta function, introduced in 1859 by Bernhard Riemann. Riemann extended earlier work by Euler, who had shown that the zeta function can be expressed both as a sum over integers and as a product over primes. Zeta of s equals the sum of n equals 1 to infinity 1 over an s equals the product of p1 over 1 minus p to the power of minus s. Zeta of s equals n equals 1 sum from infinity. ns1 equals p product 1 minus p minus s1. This identity links the additive structure of integers with the multiplicative structure of primes. It implies that understanding the analytic properties of zeta, s, reveals information about primes. Riemann proposed that the zeros of the zeta function, values of ss where zeta of s equals 0, zeta of s equals 0, govern the fluctuations in prime distribution. In particular, he conjectured that all non-trivial zeros lie on a critical line in the complex plane where the real part equals 1/2. This statement, known today as the Riemann hypothesis, remains unproven. However, for the prime number theorem, a weaker result was sufficient. Hadamard and de la Vallée-Poussin proved that the zeta function has no zeros on the line where the real part equals 1. This fact allowed them to control certain integrals and estimate the growth of prime-counting functions. The proof was not elementary. It required complex analysis, contour integration, analytic continuation, and careful bounding of error terms. It demonstrated that prime distribution is deeply connected to the analytic structure of the zeta function. The core idea is that the absence of zeros on the real part 1 line prevents certain oscillations in prime density from becoming too large. This control ensures that pi, n follows the smooth curve dictated by n over ln, n over ln, n asymptotically. The result was celebrated as a major triumph. After more than a century of conjecture and partial progress, the law governing prime density was confirmed rigorously. It is worth emphasizing what the theorem does and does not claim. It does not provide an exact formula for the nth prime. It does not eliminate irregular gaps. It does not resolve whether infinitely many twin primes exist. It describes average behavior across large scales. If one examines primes around 1 million, the average gap between consecutive primes is approximately ln of 1 million ln of 1 million, which is about 13.8. Some gaps are smaller, some larger, but on average, spacing follows this logarithmic growth. The theorem formalizes that average behavior. Another important detail concerns error terms. While pi, n, approximately n over ln, n, pm, n, minus n over ln, n, describes the leading term, mathematicians are also interested in how large the difference pi, n, minus n over ln, n, can be. Later research refined estimates for this error term. If the Riemann hypothesis were proven true, it would imply a very tight bound on that difference. Thus, even after the prime number theorem was proven, the story of primes remained incomplete. Looking back to Gauss's teenage insight, the gap between conjecture and proof spans more than a century. He recognized the correct leading behavior long before analytic methods could justify it. His diary entry did not mention the zeta function. It did not anticipate complex contour integrals. It recorded the pattern visible in data. The proof required a transformation of number theory into analytic territory. The development of complex analysis in the 19th century made this transformation possible. Functions of complex variables, initially studied for their intrinsic mathematical interest, became tools for understanding prime numbers. Hadamard and de la Vallée-Poussin's independent proofs marked a turning point. They confirmed that primes obey a precise asymptotic law. The irregularities that had frustrated mathematicians for centuries fit within a smooth global structure. The proof also demonstrated a broader principle. Discrete arithmetic phenomena can be governed by continuous analytic laws. Prime numbers, defined through divisibility of integers, obey a distribution determined by properties of complex functions. This synthesis between discrete and continuous mathematics became a defining feature of analytic number theory. When news of the proof circulated, it confirmed a conjecture that Gauss had formulated in youth. Though he had not published the original observation formally, his correspondence made clear that he had anticipated the result. In this sense, the prime number theorem's proof was both a culmination and a validation. It confirmed what careful counting and analytic intuition had suggested decades earlier. The focus now shifts from historical development to consequence. Once the logarithmic law was established, what did it mean for mathematics more broadly? How did this understanding influence later research and modern applications, from pure theory to cryptography and computing? When Carl Friedrich Gauss examined tables of prime numbers as a teenager and concluded that their density follows a logarithmic law, he was not thinking about digital security, encrypted communication, or global financial systems. He was investigating a structural question about integers. Yet the law he identified, the asymptotic behavior of prime distribution, remains central to modern mathematics and technology. To understand why this discovery still matters, it helps to separate two levels of importance, theoretical and practical. On the theoretical side, the prime number theorem reshaped number theory. Before it was proven, primes appeared erratic. After the theorem, mathematicians understood that primes obey a precise large-scale law. This changed how researchers approached related problems. The theorem establishes that the average gap between primes near a large number n is approximately ln. N. That fact alone provides a framework for estimating how frequently primes appear within any large interval. Without such a law, researchers would lack reliable expectations about prime density. For example, suppose one wants to know how many primes lie between 1 million and 2 million. The theorem allows an approximation using integrals or logarithmic estimates. While exact counts require computation, the law provides predictive guidance. Beyond simple estimation, the theorem influences the study of error terms. Once it was proven that pi n approximately equals n ln n, pi n approximately equals ln n, the next question became, how large can the difference pi n minus n over ln n, pi n minus n over ln n be? Controlling this difference leads directly into deeper territory, including the still unsolved Riemann hypothesis proposed by Bernhard Riemann. The Riemann hypothesis asserts that all non-trivial zeros of the zeta function lie on a specific vertical line in the complex plane. If true, it would imply very tight bounds on the fluctuations of prime distribution. In other words, it would refine Gauss's teenage insight into a far more precise statement. Thus, the prime number theorem is not an endpoint. It is a foundation. Much of modern analytic number theory builds upon it. There is also a conceptual importance. The theorem demonstrates that discrete arithmetic objects can obey continuous analytic laws. Prime numbers are indivisible integers, yet their collective behavior aligns with a smooth function involving logarithms. This bridge between discrete and continuous mathematics has influenced numerous areas of research. For example, probabilistic number theory models primes as though they behave like random variables, with density 1 over the natural logarithm of n, 1 over the natural logarithm of n. Although primes are not random, statistical methods provide surprisingly accurate predictions for many questions. This probabilistic viewpoint traces directly back to the logarithmic law. Now consider the practical dimension. Prime numbers are fundamental to modern cryptography. Many encryption systems rely on the difficulty of factoring large composite numbers into primes. If primes were extremely rare, or followed a simple predictable pattern, secure encryption might not be possible. In the 1970s, public key cryptography emerged, including the RSA algorithm developed by Ron Rivest, Adi Shamir, and Leonard Adleman. RSA security depends on the ability to generate large prime numbers and the practical difficulty of factoring their products. The prime number theorem plays a role in understanding how often primes appear among large integers. When generating random large numbers for cryptographic keys, one expects to encounter a prime roughly every len, n, numbers near n. This expectation allows efficient prime generation algorithms. For instance, if one is searching for a 1024-bit prime number, an integer with roughly 300 decimal digits, the theorem predicts approximately how many random candidates must be tested before finding one. The average gap near such magnitudes is on the order of ln, n, which while large remains manageable computationally. Without the logarithmic law, predicting the feasibility of prime-based encryption would be uncertain. Furthermore, modern primality testing algorithms, though sophisticated, rely on statistical expectations informed by prime density. The theorem assures that primes do not become so sparse as to make large-scale key generation impractical. Another domain influenced by prime distribution is computational number theory. Algorithms for factoring, primality testing, and cryptographic key design all depend on an understanding of how primes behave in large ranges. Even outside cryptography, primes influence pseudo-random number generation, hashing functions, and error-correcting codes. The statistical distribution of primes underlies performance guarantees in these systems. Returning to theory, the prime number theorem also serves as a template for generalizations. Mathematicians study primes in arithmetic progressions, leading to Dirichlet's theorem and further analytic results. They examine primes in short intervals, primes represented by polynomials, and primes within algebraic number fields. Each of these investigations extends the idea that prime distribution follows structured asymptotic laws. The theorem also demonstrates the power of analytic continuation and complex analysis in solving purely arithmetic problems. When Jacques Adama and Charles-Jean de la Vallée-Poussin proved the theorem in 1896, they did so using complex function theory. Their work confirmed that the structure Gauss identified numerically could be derived from deep analytic principles. This interplay between analysis and arithmetic continues today. Entire research programs revolve around extending analytic methods to new, number-theoretic questions. There is also an educational dimension. The prime number theorem often serves as a milestone in advanced mathematics courses. It illustrates how empirical observation, conjecture, and rigorous proof interact over long periods. It demonstrates that deep truths can be sensed long before they are formally established. The story, beginning with a 15-year-old in Brunswick, underscores how mathematical ideas evolve across generations. Gauss's private note became a public theorem more than a century later. That trajectory illustrates the cumulative nature of mathematics. In addition, the theorem influences how mathematicians think about infinity. Infinite sets can behave in structured ways. The set of primes is infinite, yet its density decreases predictably. Infinity does not imply disorder. Understanding prime distribution also clarifies the limitations of prediction. While average behavior is governed by logarithms, individual primes remain unpredictable. There is no simple formula generating all primes and only primes. The coexistence of global law and local irregularity is a central theme in modern mathematics. In recent decades, computational advances have allowed verification of the prime number theorem at enormous scales. Billions and trillions of primes have been counted and compared with logarithmic approximations. The convergence predicted by the theorem is confirmed numerically to extraordinary precision. Yet despite this confirmation, mysteries remain. The Riemann hypothesis continues to stand unresolved. Questions about twin primes, prime gaps, and distribution in specific sequences persist. The prime number theorem does not close the field, it anchors it. From a broader perspective, the discovery that primes follow a logarithmic law reveals something fundamental about structure in mathematics. Simple definitions can generate complex behavior governed by elegant laws. Patterns that resist local description may submit to global analysis. The insight Gauss recorded as a teenager continues to shape research, computation, and technology. It informs secure communication systems, it guides algorithm design, it motivates deep theoretical exploration. Prime numbers remain essential, not only because they are building blocks of integers, but because their distribution reveals how arithmetic and analysis intersect. As we approach the end of this exploration, it becomes natural to reflect not just on the theorem itself, but on the context in which it first emerged. A young student studying tables of numbers, recognizing order where others saw irregularity, and writing down an idea that would take more than a century to prove. In the early 1790s, in a modest German state far from the major scientific capitals of Europe, a teenager sat with sheets of numbers and asked a question that had resisted precise answer for more than 2,000 years. Carl Friedrich Gauss was not yet the mathematician history would later call the Prince of Mathematicians. He was a student with access to tables of primes, logarithmic tables, and a habit of examining patterns carefully. The question he confronted was not whether primes exist infinitely. That had been settled by Euclid in antiquity. The question was subtler. How are those infinitely many primes distributed along the number line? Infinity can be an abstract concept. It guarantees continuation without providing structure. Saying there are infinitely many primes does not indicate how frequently they appear among large numbers. It does not reveal whether they thin out rapidly or gradually, whether their gaps grow unpredictably or according to some rule. Gauss's contribution as a teenager was to see that infinity, in this case, obeys a law. By counting primes below increasing thresholds and comparing those counts with logarithmic functions, he recognized that the density of primes near a large number n behaves approximately like 1 over the natural logarithm of n1 over the natural logarithm of n. That recognition transformed infinity from a vague notion into a measurable trend. To grasp the scale of this insight, consider what it implies. If the average gap between primes near nn is roughly ln, n, ln, n, then primes never disappear. They grow sparser, but only logarithmically. Even at enormous magnitudes, numbers with hundreds or thousands of digits, primes remain present with predictable frequency. This behavior balances scarcity and persistence. Primes become rarer, but not too quickly. Their density decreases slowly enough that infinity retains structure. A 15-year-old identifying this balance is not merely performing calculation. He is reshaping how infinity is understood within arithmetic. There is also a lesson about perspective. Individual primes appear irregular. Long stretches without primes occur. Clusters appear unexpectedly. If one focuses only on local behavior, randomness seems dominant. Gauss shifted attention to cumulative behavior. Instead of asking where the next prime lies, he asked how many primes lie below a given bound. That change in viewpoint reveals smooth structure behind irregular detail. This duality, local unpredictability combined with global order, remains one of the defining features of prime numbers. The Prime Number Theorem, eventually proven in 1896 by Jacques Hadamard and Charles-Jean de la Vallée-Poussin, confirmed rigorously what Gauss had sensed. Pi, n, approximately n over ln, n, pi, n, approximately n over ln, n. Yet the proof required analytic machinery unavailable in his youth. Complex analysis, the Riemann zeta function introduced by Bernhard Riemann, and careful control of error terms were necessary to establish the theorem formally. Gauss did not wait for those tools to exist before recognizing the pattern. He trusted disciplined computation and analytic intuition. It is easy to view this story as a narrative of genius, but it is also a narrative of method. Gauss counted, he compared, he refined approximations, he did not claim more than evidence supported. His diary entry was brief and cautious. The infinity he encountered was not mystical. It was numerical. Tables extended upward. Ratios shifted gradually. logarithms provided scale. When we consider infinity in mathematics, we often imagine vast abstraction. Here, infinity revealed itself through careful tabulation and asymptotic reasoning. The significance of this moment extends beyond number theory. It illustrates how mathematical discovery can emerge from simple tools applied persistently. No advanced equipment was required, no experimental apparatus, only arithmetic, logarithms, and attention. The teenage Gauss did not close the problem of prime distribution. He opened it in a new direction. His insight guided later mathematicians toward analytic methods capable of proof. Even today, the story continues. The prime number theorem is established, but related questions remain unresolved. The Riemann hypothesis concerning the zeros of the zeta function remains one of the most important open problems in mathematics. It would sharpen our understanding of prime fluctuations if solved. Prime numbers continue to influence cryptography, computation, and theoretical research. Their distribution, governed by logarithmic law, underpins secure digital communication worldwide. When Gauss examined his tables, he could not foresee these applications. He was motivated by structure, not utility. There is something instructive about that. The law of primes emerged from curiosity about pattern, not from practical demand. Yet centuries later, that curiosity supports global information systems. The image that remains is simple. A student in Brunswick examining rows of numbers, calculating ratios, noticing convergence. Infinity was not overwhelming, it was gradual, logarithmic. The journey from that notebook entry to a fully proven theorem spanned more than a century. It required collaboration across generations. But the essential idea began with a careful observation made at 15. Prime numbers still extend without bound. Their gaps continue to widen slowly. Their density continues to follow the curve Gauss identified. The relationship between a finite mind and an infinite sequence remains grounded in method. Count what can be counted, compare carefully, and recognize when a pattern persists beyond coincidence. From that perspective, the discovery was not a dramatic revelation but a disciplined conclusion. A teenager confronted infinity and found that it obeys a law.